Imagine for a moment that the long-held notion of planets simply growing and evolving through natural cosmic processes is upended. What if instead they are meticulously planted in the fabric of the galaxy? For decades, scientists have been confounded by the rapid emergence of massive gas giants orbiting distant stars, their formation seeming almost instantaneous given the vast expanses of space and the slow process of accretion they envisioned. Just when this mystery seemed insurmountable, a remarkable discovery arrived: 3I Atlas, a solitary object drifting silently through interstellar space, bearing a chemical signature that reads like a set of cosmic instructions, an interstellar blueprint. This wandering celestial seed appears to carry all the precise ingredients necessary to ignite planetary birth, almost as if it were crafted explicitly for this purpose. Yet what makes this object truly captivating and even unsettling is that beyond its chemical makeup, there's something else aboard this cosmic seed that sparks the imagination of even the most skeptical astronomers. Could there be life inside? Could it be an organic entity, a living machine, or perhaps something entirely different? The evidence we have collected points to three distinct possibilities, each more extraordinary than the last. First, it could be a dormant microbe, an ancient, resilient organism lying in wait within the object's core. Second, it might be a piece of engineered technology, an artifact of an alien intelligence carefully disguised as cosmic debris, perhaps sent here deliberately. Third, it could be an actual biological or living seed, an entity carrying within it the blueprints for worlds still to come, perhaps even a vessel for cosmic seeding or terraforming. To unravel this enigma, we are compelled to rigorously test each of these hypotheses against the mounting evidence, following the trail of data wherever it might lead, even if that path challenges everything we have previously believed about planetary formation and the nature of celestial objects. Let us begin by establishing the basic facts. 3I Atlas is presently the third confirmed interstellar object ever detected by humanity. Discovered by the Atlas survey team stationed in Rio Hurtado, Chile, on July 1, 2025, it immediately raised eyebrows. This object's trajectory is hyperbolic, meaning it is not gravitationally bound to our sun. It travels through our solar system on a path that confirms its interstellar origin. Fortunately for us, it poses no imminent threat. Its closest approach to Earth will be roughly 1.8 astronomical units, or about 170 million miles on December 19, 2025. Now here's where things become particularly intriguing. The timeline of its passage appears almost choreographed, a celestial dance that seems too precisely timed to be coincidental. On October 3, 2025, it will pass near Mars at approximately 30 million kilometers away. Later, on October 29th, it reaches perihelion, its closest point to the Sun, at about 1.36 astronomical units, positioned behind the Sun from Earth's perspective. Then, on March 16, 2026, it will make a close approach to Jupiter, at just 0.36 astronomical units, roughly one-third of the distance from the Sun to Jupiter itself. These waypoints present an unprecedented opportunity for observation. Spacecraft orbiting Mars are poised and ready, and assets orbiting Jupiter, if planned properly, may also be able to gather vital data. The cosmic clockwork seems almost too perfect, too orchestrated, prompting questions about whether there is some hidden purpose behind its trajectory. As our investigation deepens, we encounter anomalies that refuse to fit neatly into our existing classification of comets, asteroids, or space debris. Notably, a gas coma dominated by carbon dioxide is emerging, a striking contrast to the typical water vapor-rich atmospheres we associate with familiar comets. This unusual chemistry defies our expectations and hints at something far more exotic or engineered within this interstellar visitor. The detection of early hydroxyl emissions, indicating the dissociation of water molecules, emerges surprisingly far from the sun's warming influence, an observation that defies our conventional understanding of cometary behavior. Typically, we expect such activity to occur as objects approach the sun, driven by thermal heating that sublimates surface ices, but here, the signature appears well beyond the expected activation zone. Meanwhile, a dust plume facing the sun produces what some have dubbed a forward glow, a luminous feature that challenges standard models of cosmic debris, which predict more symmetrical or trailing dust emissions rather than a pronounced sunward brightness. Adding to the mystery, spectroscopic analyses reveal signatures of nickel within the object's emitted light, yet iron lines remain frustratingly faint or entirely absent. This unusual metal ratio stands out because in the known solar system comets, iron typically dominates the emission spectra alongside nickel. The polarization behavior of scattered sunlight adds yet another layer of peculiarity. The patterns do not match those of familiar comets, displaying scattering properties that diverge from established signatures observed within our own planetary neighborhood. Individually, each anomaly might be dismissed as curiosity or observational noise, but collectively they form a coherent pattern that demands explanation. This is no ordinary comet drifting passively through space. Its peculiarities compel us to reconsider fundamental assumptions about small bodies in the cosmos. If this object, dubbed 3I Atlas, is of natural origin, it compels us to rethink how and where comets form in the cold, distant reaches between stars, regions characterized by frigid temperatures and sparse materials. Alternatively, if it represents a planetary seed, a core perhaps manufactured or deliberately placed, then it challenges our timeline of planetary formation itself, suggesting that worlds might be built from preformed building blocks, ready for capture by young stellar systems. And if, by some extraordinary possibility, it was engineered or intentionally sent as an artifact, perhaps a probe or a tool, then we are standing on the cusp of history's most momentous discovery. Evidence of intelligence or deliberate cosmic engineering. To navigate these possibilities, scientists pledge to conduct a fair and rigorous examination, carefully separating measurable facts from speculative interpretations and clearly marking hypotheses as such. The scientific community approaches such extraordinary claims with deep skepticism, rightly so, because history has repeatedly shown that anomalous observations can often have natural explanations. Expert pushback and critical analysis will be integral, ensuring that all anomalous data are considered within the broad framework of physics and astrophysics, including understanding what it truly means for an object to be interstellar. These objects, traveling at high velocities relative to local stellar motion, follow hyperbolic trajectories with eccentricities far exceeding 1, indicating they are not gravitationally bound to our sun. Most interstellar visitors pass through our solar system unnoticed, discovered only after they have already departed, if discovered at all. The early identification of 3I Atlas, however, changes everything. It marks a shift from the typical pattern of fleeting interstellar intruders to an unprecedented opportunity for coordinated observation. Campaigns now unfold using humanity's most advanced telescopes and instruments, including the Hubble Space Telescope, the James Webb Space Telescope, and observatories around the globe, some stationed within our solar system, to monitor this enigmatic visitor. If 3I Atlas is indeed a seed, either a naturally evolved cosmic gardener or a product of intelligence, what might it be seeding? Could it carry the ingredients necessary for life or even dormant life itself lying in wait for the right cosmic environment to awaken? Might it be a biological passenger, a kind of galactic courier awaiting its chance to revive and proliferate within a young star's warmth? These questions cross disciplines, blending biology with astronomy, planetary science with the search for extraterrestrial intelligence. Suddenly, the hunt is not just for radio signals from distant civilizations, but for physical artifacts drifting silently through our own neighborhood. By the time this investigation concludes, 3 plausible explanations will emerge, each supported by different strands of evidence, and it will be up to us, the scientific community and the broader public, to weigh the testimony and decide which scenario aligns most convincingly with the facts. Is it a natural object, formed through processes we understand but with unusual chemistry? Could it be a seed, an artificial core or pre-planetary structure deliberately placed or ejected by some unknown intelligence? Or might it be an artifact, a probe, a message, or a tool deliberately sent across the cosmos? The answers, profound and potentially transformative, await careful scientific scrutiny. Will you accept that this interstellar visitor was simply a product of natural cosmic processes? Or are you willing to entertain the bold, revolutionary idea that it might be part of a grand cosmic seeding, either by natural mechanisms or deliberate engineering? Perhaps instead you'll find yourself confronting the most profound and startling possibility of all, that an intelligent civilization has reached out, cloaked in the guise of a humble comet, silently observing from the shadows of the galaxy. The moments are ticking away, bringing us closer to our first significant observational milestone. In just a matter of weeks, Mars will come into close proximity with this mysterious object, offering an unprecedented opportunity for direct high-resolution study. Beyond our star, behind the sun's blinding brilliance, perihelion, the closest approach, looms like a final act on a stage where the curtain may finally lift on answers long sought. As the evidence steadily accumulates and competing theories clash, somewhere in the vast darkness between the stars, other wanderers drift through the cosmic void, each on a rendezvous with destiny that might forever change our understanding of the universe. But before we reach that pivotal moment, we must scrutinize the claim echoing loudly through both the halls of science and the corridors of social discourse. A claim that refuses to whisper in hushed tones and instead demands to be heard. This is the hypothesis that boldly challenges the status quo, insisting that what we see might not be merely natural. Instead, it could be an artifact, a deliberate message, or a technological seed from an intelligence far beyond our current comprehension. Part 2. The Alien Hypothesis. This notion arrives not with subtlety or quiet suspicion, but with the confident assertion of one of the most respected astrophysicists of our time, Abraham Loeb of Harvard University. Known for his pioneering work on black holes and the large-scale structure of the cosmos, Loeb's interpretation of the interstellar object known as 3I Atlas has ignited intense debate across the scientific community. With rigorous mathematical reasoning, he argues that the object's unusual trajectory and properties might be more than mere chance. Loeb draws attention to the object's remarkably precise alignment with the plane of our solar system's planets, a pattern that, under his calculations, has an exceedingly low probability of occurring randomly. The object's path is almost too orderly, almost too familiar, traversing a sequence of encounters with planetary zones that seem to suggest a reconnaissance mission, as if designed by an intelligent agency. First Mars, then Venus at a greater distance, followed by a distant approach near Earth, and finally a close pass by Jupiter. A route that reads like a carefully plotted survey, a cosmic checklist executed with deliberate purpose. He estimates that the chance of such an alignment happening purely by accident is roughly a mere 5 in 100,000, an improbability that commands serious consideration. This is not a consensus view, but the mathematical framework Loeb offers compels us to examine the possibilities with an open mind. Loeb's second piece of evidence revolves around what he calls the forward glow, the cigar-shaped brightness profile of the object as it faces the sun. To him, this pattern appears deeply suspicious, hinting at something unnatural. Yet when the Hubble Space Telescope analyzed the object, the picture became more complex. Its observations revealed a more nuanced reality, a dust plume facing the sun, driven by heating, along with a faint tail extending in the opposite direction. Behaviors consistent with well-understood comet physics. This asymmetry, driven by the physics of sublimation and outgassing, can naturally produce the sun-facing brightness fans Loeb describes. The challenge is separating the raw, peer-reviewed data from speculative interpretations. The fact remains that the sunward brightness has been confirmed by multiple telescopes, but whether this pattern points to a natural process or an engineered design remains fiercely debated within scientific circles. In essence, the physical evidence of a brightness fan facing the sun exists. The controversy lies in what it signifies, whether it is a product of natural physics or a sign of artificial intent. That debate continues to ignite passionate discussions, but at this stage the core facts remain. Multiple observations support the existence of this sunward glow, leaving the question open as to whether it is a natural phenomenon or something more extraordinary. The narrative surrounding the detection of nickel in Interstellar Object 3 Atlas becomes increasingly intricate once subjected to careful scrutiny. Observations made with some of the world's most powerful telescopes, specifically utilizing ultraviolet and visual spectrographs aboard large observatories, revealed emission lines characteristic of neutral nickel atoms. Interestingly, in the same spectral data, signatures of iron, an element often associated with cosmic dust and planetary materials, were conspicuously absent. Loeb and other astronomers have proposed that this particular pattern might point toward processed metals, materials that could have undergone industrial refinement, alloying, or metallurgical processing rather than forming naturally through cosmic chemistry. Such a conclusion, if true, would suggest an artificial or at least technologically influenced origin of the metal signatures. However, the absence of detectable iron does not necessarily mean that iron is entirely absent. It could simply be present below the current detection thresholds of our instruments. Alternatively, the physical conditions around the object, such as excitation states, local temperature, or radiation fields, might favor nickel emission over iron, making nickel lines more prominent even if iron exists in similar quantities. It's worth noting that previous comets within our solar system have occasionally exhibited nickel signatures in their spectra without raising concerns of extraterrestrial manufacturing or artificial origin. These signatures can naturally occur due to cosmic dust and native planetary materials, and their presence alone does not constitute evidence of deliberate engineering or alien technology. The leap from observing unusual metal ratios to asserting an industrial or artificial origin demands an extraordinarily high level of justification, what scientists refer to as extraordinary evidence to support extraordinary claims. This is where Loeb's line of reasoning ventures into darker and more speculative territory. Borrowing from science fiction's dark forest hypothesis, a metaphor suggesting that advanced civilizations might conceal their presence for survival, Loeb hypothesizes that the peculiar metal signatures could be part of an intentional strategy to hide or mask the object's true nature. He suggests that if 3 Atlas is in fact a reconnaissance probe sent by an extraterrestrial civilization, then its perihelion passage, its closest approach to the sun, would likely be strategically timed behind the sun from Earth's perspective. Such a positioning would minimize our ability to observe it directly, effectively shrouding its activities from our detection efforts. The timing of this event appears from our vantage point to be unusually opaque, almost deliberately arranged to evade scrutiny. This interpretation assumes that the probe was intentionally designed with sophisticated concealment tactics, perhaps employing orbital maneuvers, course corrections, or other subtle orbital mechanics. Yet current observational data do not show any signs of course adjustments or maneuvering that would indicate active tampering or steering. Nonetheless, Loeb posits that an advanced extraterrestrial technology might operate below the detection thresholds of our instruments, employing methods or systems that are simply too subtle or advanced for our current observational capabilities. Loeb and his collaborators, including Hibbert and Crowell, have explored a broad spectrum of scenarios, ranging from the passive collection of data to potentially hostile intentions by such a probe. They speculate about its capabilities, its data collection objectives, and even suggest that it might pose a threat to human civilization if it were of artificial origin and harboring malicious intent. However, these ideas have sparked fierce criticism within the astronomical community. Many experts dismiss such speculative scenarios as baseless and fear-mongering, emphasizing the lack of concrete evidence to support claims of extraterrestrial engineering or hostile intent. This pushback reflects a fundamental tension within the field of astronomy itself. The challenge of balancing healthy skepticism with open-minded inquiry. The question arises, how far should scientists venture into such speculative territory? When does cautious skepticism become rigid orthodoxy that dismisses intriguing anomalies? Conversely, when does curiosity cross into irresponsible sensationalism? In the search for genuine techno-signatures, indicators of alien technology, certain observational criteria are considered essential. For instance, persistent non-gravitational accelerations that cannot be explained by known physics of sublimation or natural outgassing would be a strong red flag. Similarly, brightness variations that follow programmed rather than rotational patterns or structured repeating jet emissions could suggest active attitude control or deliberate signaling. The detection of narrowband radio or optical emissions, wavelengths often associated with technological activity, would be considered definitive evidence of artificial origin. Thus far, none of these smoking guns have appeared in the observational data for 3 Atlas. The object continues to behave remarkably like a typical comet, albeit an unusual one. It outgasses, develops a coma, and exhibits dust emission patterns that are consistent with solar heating. Behaviors that follow well-understood physical principles. It adheres precisely to gravitational mechanics, with no detectable deviations that would hint at artificial propulsion or manipulation. The alien hypothesis, despite its allure, faces its greatest obstacle: the need for extraordinary proof. As Carl Sagan famously stated, extraordinary claims require extraordinary evidence. While the peculiar metal signatures and timing might raise eyebrows and inspire speculation, they do not, at this moment, constitute Loeb's mathematical reasoning concerning the probabilities of a trajectory. While undeniably intriguing and thought-provoking, does not, in itself, serve as definitive proof of an artificial origin. The core issue lies in the fact that statistical improbability on its own cannot reliably distinguish between a purposeful design and a mere natural coincidence, especially when considering isolated events rather than repeated or reproducible phenomena. In the scientific community, a cautious approach prevails, rooted in the understanding that premature conclusions, particularly about extraterrestrial technology, could have far-reaching consequences. Declaring an object as an alien artifact without solid conclusive evidence risks eroding public trust in astronomical research and SETI efforts, potentially setting the field back decades. This cautious stance isn't born from skepticism alone, but is a necessary safeguard, learned through hard experience. The scientific community has faced similar pitfalls in the past, such as the initial excitement over pulsars, fast radio bursts, and other anomalies that initially appeared to be artificial signals but ultimately revealed natural origins. Interestingly, Loeb's persistent advocacy and hypotheses, despite their controversial nature, have catalyzed valuable scientific activity. His bold ideas have spurred comprehensive observational campaigns, pushed the development of innovative analytical techniques, and compelled researchers to precisely define what constitutes convincing evidence of artificiality. Even hypotheses that are ultimately proven false serve an important function. They sharpen our investigative tools, clarify what kinds of signatures or patterns are truly indicative of non-natural origins, and expand our understanding of the limits of current technology and knowledge. This discussion also underscores our profound lack of knowledge about the population of interstellar objects. To date, humanity has confirmed only 3 such visitors. One, named Oumuamua, a second, Borisov, and now a third, the object designated as 3 Atlas. Drawing broad conclusions from such a tiny sample is inherently risky, as it leaves ample room for error and misinterpretation. What appears anomalous or extraordinary today might, with the expansion of our detection capabilities and scientific understanding, become a common feature of interstellar objects tomorrow. As our sensing and analytical methods improve, so too will our ability to interpret these visitors, potentially revealing that what once seemed unusual is actually typical. The implications of these questions extend far beyond the technical realm into philosophical considerations. If in the future evidence were to confirm that 3 Atlas is indeed an artificial construct, it would represent the most groundbreaking discovery in human history. Such a revelation would fundamentally challenge our assumptions about our cosmic isolation, suggesting that intelligent life or advanced civilizations are more interconnected and active across the galaxy than previously thought. All current strategies for SETI and planetary defense would need to be re-evaluated and possibly overhauled. Our understanding of the universe and our place within it would be irrevocably altered. Yet, despite the intense efforts and months of rigorous observation, conclusive proof remains frustratingly out of reach. The collective evidence, while hinting at the possibility of a natural origin, albeit with chemistry and physics that are more exotic than those of typical solar system comets, continues to point toward a natural explanation. Moving forward, the hypothesis of artificiality functions as a critical benchmark, a standard against which all new data are measured. Every anomaly is scrutinized through this lens, and every dataset is examined meticulously for signs of technological signatures or artificial processes. Most scientists anticipate that the hypothesis of artificiality will ultimately be rejected, most likely because the evidence does not support it. This expectation, however, is not based on dismissiveness but on the desire for proof grounded in reproducibility and rigor. If the object truly were artificial, clear, and convincing evidence, such as systematic non-gravitational accelerations incompatible with natural outgassing, narrowband emissions indicative of technology, or structured jet activity inconsistent with physical expectations, would need to be observed and verified independently. Until such unambiguous signs emerge, the scientific consensus remains rooted in a natural origin hypothesis. The behavior of 3 Atlas in particular offers rich insights. Its activity tells a story, one that depends critically on how we interpret the complex and often contradictory data pouring in from telescopes and spacecraft. The third part of this investigation focuses on the evidence of activity itself. The first to deliver a significant surprise was the ultraviolet observations from the Swift Observatory, which revealed behaviors that challenged traditional comet models. Notably, hydroxyl emissions, an unmistakable signature of water vapor dissociation, were detected at approximately trajectories astronomical units from the Sun. This is a pivotal finding because in standard cometary physics, such activity usually occurs much closer to the Sun, as solar heating drives sublimation of ices. The presence of water dissociation signatures at such a distance implies that this object is exhibiting active behavior far beyond the expected zone, prompting new questions about its composition, structure, and perhaps even its origins. The detection of 3I Atlas at such a considerable distance places it significantly beyond the conventional activation zone, where solar heating typically stimulates the sublimation of cometary volatile substances. To truly grasp the importance of this anomaly, it's helpful to compare it to the behavior of most comets within our solar system. Usually, these icy wanderers remain dormant and inactive until they approach within about 3 astronomical units of the Sun, at which point solar warmth ignites their stored volatiles, creating observable comas and tails. However, 3I Atlas was already venting water vapor long before crossing this critical threshold, implying either an unconventional internal composition or the presence of exotic sublimation physics at play. This early water activity suggests a porous, volatile-rich interior that responds to even modest solar warming, indicating a surface or subsurface environment more reactive than typical. Adding to this intriguing picture, the team behind the James Webb Space Telescope's near-infrared spectrograph delivered a startling revelation. Their detailed analysis uncovered a carbon dioxide to water ratio of roughly 8:1, a stark contrast to what we observe in most familiar solar system comets, where water overwhelmingly dominates the volatile inventory and carbon dioxide plays a secondary role. This reversed ratio situates 3I Atlas firmly within uncharted chemical territory. Such a composition implies it formed under conditions very different from those of the comets we know, likely in environments that are much colder and richer in carbon dioxide. It's plausible that this object condensed in the outermost regions of a different stellar system, where conditions favored the freeze-out of carbon dioxide over water ice. Alternatively, the unusual chemistry could be the result of thermal processing during its long interstellar journey. Over geological timescales, cosmic ray bombardment and encounters with other stars could alter the surface and subsurface composition, modifying the original volatile ratios. Although the precise mechanisms behind these alterations remain speculative, the chemical fingerprint of 3I Atlas unmistakably marks it as distinct from local solar system comet populations. Further clues come from spectroscopic detection of cyanogen, CN emission lines, which bolster the active comet interpretation while enriching the chemical inventory. These CN signatures are often linked to the sublimation of organic compounds, suggesting that 3I Atlas harbors complex carbon-nitrogen chemistry within its nucleus. This detection is significant because it helps astronomers delineate chemical boundaries as the object approaches the Sun, providing vital constraints on sublimation physics and the physical and chemical nature of its surface and interior. Perhaps the most captivating anomaly arises from polarimetric measurements. Early observations revealed an unusually strong and extended negative polarization branch, indicating that light scattering by dust particles in the coma occurs in ways that differ markedly from most solar system comets. This optical behavior hints at dust grains with exotic properties, unusual size distributions, high porosity levels, or distinct compositional features that influence how sunlight interacts with the coma material. Since polarization is a highly sensitive probe of dust physics, these signatures suggest that the particles composing 3I Atlas's dust environment are unlike anything previously observed, possibly reflecting unique formation processes or evolutionary histories that diverge from familiar cometary environments. High-resolution imagery from the Hubble Space Telescope further clarified the forward glow phenomenon. It precisely resolved the dust and gas emission patterns, confirming that the unusual scattering and polarization signatures are indeed linked to the physical properties of the dust grains and their interaction with solar radiation. These insights collectively deepen the mystery surrounding this interstellar object, revealing a complex interplay of chemistry, physics, and history that challenges existing models and expands our understanding of the diversity of icy bodies drifting through our galaxy. High-resolution imaging of the interstellar object reveals a distinctive dust plume emanating from its sun-facing hemisphere. This feature is driven by asymmetric heating, where one side absorbs more solar energy, causing localized outgassing that pushes dust outward. Complementing this, a faint tail extends in the opposite direction of the sun, precisely aligning with what we expect from natural cometary behavior. Such observations serve to dispel some of the more speculative interpretations that the object's brightness might be artificially enhanced or engineered. In natural comets, solar heating creates temperature gradients across their rotating surfaces. Warmer areas outgas more vigorously, lifting dust into space and forming characteristic tails and brightness patterns. These processes, occurring without any need for artificial intervention, can naturally produce forward-directed brightness increases, mimicking some signatures once thought to suggest artificial origin. From the images captured by the Hubble Space Telescope, size constraints come into sharper focus and serve as vital boundaries for scientific speculation. The estimates suggest that the nucleus's diameter falls somewhere between approximately 440 meters and 5.6 kilometers. Notably, this range excludes the giant Manhattan-sized descriptions that gained traction in early media reports, which often exaggerated the object's scale. This relatively modest size aligns well with expectations for interstellar wanderers. Small enough to be consistent with the population of such objects, yet large enough to dismiss the need for exotic hypotheses involving enormous, engineered constructs. Precise measurement of the nucleus's size remains challenging, especially when the active coma, the cloud of gas and dust surrounding the core, obscures the nucleus itself. Even with careful image processing and multiple observations over time, the estimates carry significant uncertainties. Nonetheless, these bounds are sufficient to guide theoretical models and allow meaningful comparisons with other known interstellar objects. The overall activity pattern of this object closely resembles that of a typical comet in many fundamental ways, with outgassing, dust emission, and brightness variability aligning with known behaviors. However, it also exhibits certain chemical and physical anomalies, unusual elemental ratios, atypical dust properties, or atypical spectral signatures that distinguish it from objects originating within our solar system. This blending of familiar physics with exotic composition presents an interpretive challenge for astronomers. It forces us to reconsider whether we are witnessing a natural phenomenon or something more engineered or artificial. So what kind of observational evidence would definitively differentiate a purely natural origin from an artificial one? Persistent thrust-like accelerations that cannot be explained by sublimation, the process where solar warmth causes volatile materials to vaporize, would be a strong indicator of artificial propulsion or control. Such accelerations would manifest as systematic deviations from the predicted gravitational trajectory, detectable through precise astrometric measurements taken over extended periods. Similarly, engineered spectral features, narrowband emissions at specific frequencies associated with technological sources or elemental ratios that defy natural chemistry, could serve as a smoking gun. However, establishing such impossible elemental or spectral ratios requires an exhaustive understanding of interstellar chemistry, knowledge that we currently do not possess. Temporal patterns in outgassing behavior might also reveal artificial control systems. Natural sublimation typically follows predictable cycles tied directly to solar heating and planetary rotation. If jets or emissions exhibit timing or intensity patterns disconnected from these natural rhythms, it could indicate deliberate active control. To date, however, none of these decisive signatures have emerged from the data. The object, known as 3I Atlas, continues to behave remarkably like a chemically unusual but fundamentally natural comet. Its activity, composition, and dynamics fit within the known framework of cometary physics, even as it challenges us with its exotic chemistry. The ongoing investigation remains open, and the absence of clear artificial signatures keeps the door open to natural explanations, though the question of origin remains an intriguing and ongoing puzzle. Anomalies, when examined closely, often remain unconvincing in their challenge to established interpretations, yet they seldom provide enough evidence to definitively overturn long-held scientific consensus. The absence of unmistakable technological signatures, the clear indicators of artificial origin, does not entirely dismiss the possibility that these objects could be engineered by advanced civilizations. It's conceivable that such technology might operate beneath our current detection thresholds, or that our conceptual frameworks are simply insufficient to recognize the subtle signatures of truly alien engineering. Nonetheless, the burden of proof remains firmly on those making extraordinary claims. Such claims necessitate extraordinary evidence. The intriguing chemical peculiarities observed in these interstellar visitors, however, do raise fundamental questions about the diversity of interstellar objects and the processes that govern their formation. If the object known as 3I Atlas truly exhibits the typical chemistry of interstellar comets, then our existing theories about the evolution of volatiles in the outer regions of planetary systems require significant revision. Its dominance of carbon dioxide and the presence of early water activity suggest it originated in an environment markedly different from the regions where our solar system's comets are believed to form. These chemical signatures could be echoes of the parent star system's unique formation history, its subsequent evolutionary path, and the mechanisms by which such objects are ejected into interstellar space. Different stars develop from molecular clouds with varying chemical compositions, and their planetary systems often undergo distinct dynamical evolutions. The specific combination of factors that resulted in the creation and subsequent ejection of 3I Atlas might be either an uncommon or a relatively frequent occurrence. Our current data simply do not suffice to determine which. As ongoing investigations shed more light, the evidence of activity associated with the object provides critical constraints on our theoretical models, yet simultaneously raises new questions about the nature of cosmic chemistry and physics. While it is clear that 3I Atlas belongs to the category of active comets, it also pushes the boundaries of this classification, stretching it in unexpected and intriguing ways. This prompts a foundational question. What could it truly mean for such an object to be alive inside? Before we can assess its plausibility with respect to the mounting evidence, we must carefully define what life entails in this context. Part 4 of this inquiry explores what alive inside might signify. When we entertain the idea that an object like 3I Atlas contains life, we must proceed with caution, navigating through 3 distinct conceptual domains. Each offers a different perspective on what life might mean when applied to an interstellar wanderer. The first interpretation embraces the most literal view, biological life in its traditional sense. This would entail microbial organisms residing within the core of the object, shielded by layers of ice and dust that serve as protection against the harsh radiation environment of interstellar space. Such a scenario demands organisms capable of surviving not only extremely low temperatures, but also relentless cosmic ray bombardment. the vacuum of space and potentially remaining in a state of dormancy for millions of years. Earth provides tantalizing examples of organisms with extraordinary resilience. Extremophile bacteria thrive in conditions once deemed impossible, from the crushing depths of ocean thermal vents to highly radioactive environments, from the icy depths beneath Antarctica's glaciers to the vacuum of low Earth orbit. Some species can enter cryptobiotic states, suspended animation, that last for decades or even longer, only to resume biological activity when conditions become favorable again. The layers of ice and dust enveloping such an object could, in theory, serve as a shield, protecting any interior microbes from lethal radiation doses during long interstellar voyages. Scientific analyses propose that several meters of frozen, icy material embedded within such objects could serve as an effective shield, substantially diminishing cosmic ray exposure to levels compatible with known biological tolerances. In the cold depths of interstellar space, this icy crust would act as a protective barrier, allowing potential microbial life to survive extended journeys through the galaxy. When these objects venture closer to stars during their orbital paths, the resulting heating could temporarily create pockets of liquid water within their porous interiors. Such transient zones of liquid could, in principle, reactivate dormant biological agents, offering brief windows during which life could resume metabolic processes before freezing temperatures or space conditions reassert dominance. It's crucial to emphasize that this biological scenario remains entirely speculative at present, lacking any direct observational evidence to confirm such processes. Nevertheless, from a physics standpoint, the idea appears marginally plausible, provided certain carefully constrained conditions are met, such as the right combination of interior porosity, thermal insulation, and heat transfer mechanisms. The key scientific questions revolve around how these objects might have initially become contaminated, whether through accidental delivery of microbes from their parent systems or other mechanisms, the timescales over which any hypothetical life could survive, and how we might detect signs of biological activity or remnants thereof. The second interpretive avenue explores the realm of biotechnology, contemplating the possibility that some of these objects could be composed of or contain self-repairing adaptive materials, systems that blur the line between living organisms and engineered devices. This concept of living technology draws inspiration from cutting-edge fields such as synthetic biology and programmable matter, where materials are designed to respond dynamically to their environment. Imagine substances that can detect damage, repair themselves autonomously, or adjust their physical and chemical properties in accordance with pre-programmed objectives. Such systems might incorporate biological components, like synthetic enzymes or genetically inspired circuits, within technological frameworks, creating hybrid entities that exhibit lifelike behaviors without being strictly biological in the traditional sense. Applied to 3 Atlas, this interpretation could provide an alternative explanation for some of its observed behaviors, such as seemingly deliberate outgassing patterns or apparent adaptive responses to solar heating. It's conceivable that the object might contain embedded self-modifying systems engineered to optimize performance across the varying environmental conditions it encounters during interstellar travel. These hypothetical systems might adjust their internal states to maximize resource utilization or to maintain structural integrity without external intervention. However, it's important to stress that, at present, no observational evidence supports the existence of such exotic, self-aware materials or systems. The idea remains firmly within the realm of speculation, though rapid advances in terrestrial biotechnology suggest that such possibilities are becoming increasingly conceivable, especially when considering the potential capabilities of sufficiently advanced extraterrestrial civilizations. As our understanding of synthetic biology, nanotechnology, and programmable matter continues to evolve, The prospect of discovering or engineering such living systems in space becomes less implausible, albeit still highly uncertain. The third scenario adopts the most radical stance, that of full artificiality. In this view, the object might be a spacecraft or probe, an engineered device deliberately disguised to resemble a natural comet. Such a scenario demands highly sophisticated engineering, capable of mimicking the physical and spectroscopic signatures of natural sublimation-driven bodies while concealing technological signatures from astronomical observation. Creating a convincing disguise would require a detailed understanding of sublimation physics, dust production mechanisms, and the spectral fingerprints of natural comets. Then engineering systems that replicate these phenomena convincingly across multiple wavelengths and observation techniques. This level of deception could serve reconnaissance purposes, allowing such a probe to observe stellar systems in detail without revealing its true nature, thus avoiding detection or defensive responses from potentially hostile civilizations. The camouflage would need to function across optical, infrared, and radio wavelengths, maintaining the illusion of natural behavior in various observational contexts. The possibility of such deception is consistent with the dark forest hypothesis in astrobiology, which posits that advanced civilizations might choose to remain invisible, fearing that revealing themselves could invite threats. The recent detection of nickel signatures, without corresponding iron signals, in the spectral data has particularly fueled speculation along these lines. Some researchers wonder whether selective metal ratios could indicate industrial processing or engineered material choices rather than natural cosmic chemistry. This suspicion arises because certain metal signatures, like nickel, are more easily associated with processed, refined materials, possibly manufactured, rather than purely primordial cosmic dust. Such metal ratios, if confirmed, might suggest the presence of artificial fabrication or deliberate manipulation, although current evidence remains inconclusive and subject to alternative natural explanations. In sum, these interpretations, ranging from biological resilience through self-repairing hybrid systems to fully artificial probes, each open profound questions about the nature of objects traversing interstellar space. While none currently have definitive observational support, the ideas push the boundaries of our scientific imagination, challenging us to develop more sophisticated detection methods and broadening our understanding of what might be possible in the universe's vast, mysterious expanse. Nevertheless, it is important to recognize that the absence of iron emission lines in particular spectral observations does not categorically confirm that iron is entirely lacking within the object. Various factors influence how elements manifest in spectra, including excitation conditions, elemental abundance ratios, and the sensitivities of detection instruments. For example, nickel emissions have been observed in previous comets without any implications of artificial origin. This suggests that unusual metal ratios alone do not constitute definitive evidence of industrial processing or extraterrestrial craftsmanship, and any such interpretive leap demands much stronger, more conclusive proof than what current data provide. The dust plume observed on the sunward side of the object, which initially appears striking, can be explained through well-understood natural phenomena, specifically asymmetric heating and rotation effects. Solar radiation naturally creates temperature gradients across the surface of the object, leading to localized heating that drives outgassing from warmer regions. The dust ejected in such processes can form patterns that produce a forward-directed brightness enhancement, a feature that might easily be mistaken for artificial activity by casual observers unfamiliar with natural cometary physics. When considering the potential habitability of 3 Atlas, the physical conditions within the object present formidable barriers to sustaining biological activity. Most likely, internal temperatures remain well below freezing throughout the majority of its trajectory through space. While brief periods of warming near encounters with stars could, in theory, generate transient liquid zones, these episodes would be short-lived, lasting only for relatively brief spans of time. The more plausible scenario is that organic chemistry rather than thriving ecosystems dominates the object's chemistry. Over extended dormancy periods, complex carbon-based compounds could undergo slow transformation reactions, gradually altering their structure in ways that might, under certain conditions, create chemical environments conducive to life if liquid water were to become available later. This leads us to a fascinating question about the nature of living technology itself. That is, systems or materials that might blur the traditional boundaries between biology and artifact. If we were to discover materials capable of growing, reproducing, adapting, and responding dynamically to environmental challenges, how would we classify them? Would they be deemed biological, technological, or some hybrid of both? The distinction might become meaningless when considering sufficiently advanced engineering approaches. For instance, programmable matter, a field actively under development in terrestrial laboratories, aims to create materials that can reconfigure and self-modify according to preset instructions. Such materials could exhibit behaviors indistinguishable from biological growth or adaptation. Applied to interstellar exploration, these capabilities could provide probes with remarkable versatility. They might autonomously adapt their configurations for different mission phases, repair damage without external intervention, or modify their behavior based on conditions discovered within target systems. Herein lies the challenge. The burden of proof for any hypothesis suggesting the presence of life, or alive inside, remains extraordinarily high. Claims involving biological systems, biotechnology, or sophisticated artificial constructs necessitate evidence that current observations simply cannot account for. While speculation plays a valuable role in broadening our conceptual horizons, motivating the development of new observational strategies and exploring theoretical possibilities, it cannot substitute for empirical proof. So what kind of evidence would convincingly support a biological hypothesis? Detectable metabolic byproducts, such as specific gases or organic molecules that are unlikely to arise through purely abiotic processes, could serve as compelling clues. Similarly, the identification of complex organic signatures that are inconsistent with known abiotic chemistry, or isotopic ratios indicative of biological processing, would strengthen the case. Ultimately, establishing the presence of life or lifelike systems within such objects requires evidence beyond mere anomalies. It demands clear, reproducible signals that cannot be explained through natural physics and chemistry alone. However, differentiating between true biological processes and abiotic organic chemistry remains one of the most notoriously challenging tasks in planetary science, even when examining samples from Earth. The complexity arises because organic molecules and chemical signatures that might hint at life can also form through purely physical and chemical processes without any biological intervention. To convincingly argue for an artificial or biological origin within an interstellar object, the evidence would need to be more conspicuous, such as narrowband electromagnetic emissions, systematic modifications in trajectory that defy natural gravitational and physical laws, or spectral features that are simply impossible to produce through any known cosmic chemistry. While it is conceivable that advanced camouflage or cloaking mechanisms could hide such signatures from our current instruments, invoking the existence of undetectable artificially engineered technology ventures into territory that is fundamentally untestable and thus unscientific, approaching unfalsifiability. The philosophical ramifications of definitively establishing the presence of life, be it microbial or otherwise, inside an interstellar object would eclipse the significance of the mere discovery itself. If biological, it could point to either a natural process of cosmic panspermia, where life spreads across the galaxy through the exchange of celestial debris, or a deliberate act of seeding by an intelligent civilization, intentionally dispersing life-bearing material into star systems. Conversely, if the evidence points toward a technological origin, it would imply that the object is a form of observation, perhaps an autonomous probe, designed for reconnaissance, evaluation, or even contact initiation, thus opening a new chapter in our understanding of extraterrestrial intelligence. Any such discovery would radically transform our perspective on the distribution of life and intelligence throughout the galaxy, challenging our assumptions and expanding the scope of astrobiology and SETI research. The potential consequences for human civilization are profound, affecting everything from planetary defense strategies to our philosophical understanding of our place in the cosmos. Such a revelation could inspire a re-evaluation of our technological capabilities, our responsibilities as cosmic explorers, and our outlook on the universe itself. Nonetheless, claims of this magnitude demand extraordinary proof, evidence that leaves no room for doubt. Currently, our observations of the object known as 3 Atlas align well with the physics and chemistry of a natural comet, even if its specific composition appears more exotic than typical examples from our solar system. As investigations continue, the concept of alive inside, whether implying biological life or complex artificial systems, serves as an important benchmark. It encourages us to remain receptive to unexpected possibilities while adhering to rigorous standards of proof. Throughout scientific history, the universe has repeatedly surprised us with phenomena that challenged prevailing understanding. Yet such surprises have always been grounded in solid evidence rather than mere speculation. While imaginative hypotheses are valuable, they push the boundaries of our knowledge. They must ultimately be supported by reproducible, verifiable data. A different, more radical idea has begun to gain traction within mainstream astronomy. The notion that cosmic seeding might be explained entirely through natural processes, without invoking life, intelligence, or technology. These explanations suggest that the chemical and material exchange between stellar systems can occur through natural mechanisms alone, providing a plausible alternative to more extraordinary claims. In fact, the official stance of the National Aeronautics and Space Administration remains unequivocal. 3 Atlas is classified as an active comet, period. No governmental or scientific agency currently endorses hypotheses involving alien technology, artificial origin, or living spacecraft. This position reflects decades of accumulated wisdom and cautious scientific judgment, cultivated through rigorous analysis and the recognition of how easily sensationalism can distort findings. Leading comet researchers have responded to the more extraordinary claims with a consistent emphasis on evidence-based skepticism, advocating for thorough examination of natural explanations before entertaining revolutionary hypotheses. Darrell Seligman of the University of Chicago, for example, champions an evidence-first approach, urging scientists to exhaust all plausible natural explanations prior to considering more exotic possibilities. Similarly, Robert Lawler from the Planetary Science Institute echoes this prudent stance, reminding us that unusual chemistry alone does not automatically point to an artificial or biological origin. Marco Michel of the European Space Agency underscores the importance of reproducibility, multiple independent observations that can be reliably repeated before any extraordinary claims are accepted as scientific fact. This cautious, methodical approach has served science well, preventing premature conclusions and safeguarding the credibility of research into interstellar phenomena. Experts in the field of astronomy are well aware that throughout history the scientific community has often been caught up in premature excitement over phenomena that initially appear to defy conventional understanding. Many of these cases serve as cautionary tales, illustrating how initial interpretations can be overly speculative until further investigation clarifies the true nature of these mysteries. For instance, pulsars, rapidly rotating neutron stars, once appeared so extraordinary that some researchers briefly entertained the provocative idea that they might be signals from extraterrestrial civilizations, akin to cosmic beacons. Similarly, fast radio bursts, which produce brief yet immensely energetic radio emissions, once seemed so implausibly powerful that their origins were questioned until advancements in theoretical models revealed natural mechanisms capable of producing such phenomena. Another notable example is Tabby's star, which exhibited highly unusual and irregular dimming patterns that initially fueled sensational speculation about the presence of alien megastructures, vast artificial constructs orbiting the star, designed to harness or manipulate its energy. However, subsequent scientific scrutiny and detailed dust cloud models eventually provided natural explanations rooted in circumstellar dust and debris, leading to a consensus that these irregularities are consistent with known astrophysical processes. This pattern of developing hypotheses, testing against accumulating evidence, and ultimately favoring natural causes has been a recurring theme in the history of astronomy. Such precedents serve as a fundamental motivation for adopting a cautious and conservative stance when analyzing the data related to 3I Atlas. The central arguments supporting claims of artificiality often rely on probability assessments, calculations attempting to estimate the likelihood that an observed object or behavior is the result of intelligent design rather than natural processes. However, these probability arguments face significant scrutiny from statisticians and methodologists. Post hoc probability calculations, those made after observing a particular outcome, are especially problematic because they are susceptible to selection bias and often involve assumptions that are carefully chosen to fit the desired narrative, sometimes cherry-picking data to support a preconceived conclusion. When dealing with a single observed event rather than a series of reproducible experiments, it becomes exceedingly difficult to distinguish a genuine anomaly from a chance fluctuation. For example, some scientists have pointed to the specific trajectory alignment of 3I Atlas as suspicious, suggesting that its orbit appears unlikely by random chance. Critics, however, argue that any particular orbital configuration will seem improbable when examined in isolation after the fact. The real question is whether this orbit signifies a meaningful deviation from what we would expect based on the limited sample size of detected interstellar objects. Given that humanity has only confirmed the existence of 3 such objects, making broad statistical inferences about what constitutes normal versus anomalous behavior is inherently risky. What appears unusual today may become commonplace as our detection capabilities improve and our catalog of interstellar visitors expands, particularly with upcoming surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time, which is expected to dramatically increase the number of identified interstellar objects. Regarding the possibility of artificial propulsion, forces that might indicate deliberate maneuvering, current measurements reveal no anomalies beyond the inherent uncertainties of our instruments. The small, non-gravitational accelerations observed in comets are well understood to originate from sublimation of volatile substances, which creates thrust-like effects. These forces tend to follow predictable patterns tied to the object's rotation, the distribution of sublimating materials, and their response to solar heating. Detecting an artificial thrust would require identifying systemic deviations from these expected physical behaviors, a challenge that remains unmet with the current data for 3I Atlas. The discussion around nickel emission lines, spectroscopic signatures detected in the object's coma, has also generated considerable debate. Some researchers have proposed that the presence of nickel without corresponding iron signals might suggest industrial processing or artificial origin. However, experts in comet chemistry caution against jumping to such conclusions, explaining that elemental emission patterns depend heavily on physical conditions such as excitation thresholds, temperature, and density. It is not uncommon for nickel to appear in the spectra of natural comets without implying any artificial or technologically manufactured source. In fact, nickel lines have been observed in other solar system comets, and their mere presence does not constitute evidence of extraterrestrial processing or engineering. Therefore, while intriguing, the nickel detection alone does not reliably serve as an indicator of artificial origin. Cosmic dust is composed of various transition metals, and their emission behaviors often depend intricately on environmental factors such as temperature, density, and the intensity and character of surrounding radiation fields. Notably, the absence of iron emission lines in certain observations should not be hastily interpreted as evidence of metallurgical processing or artificial refinement. Such a conclusion would be premature, as the lack of detectable iron could simply stem from limitations inherent in our observational techniques rather than an actual deficiency in iron within the dust particles. Moreover, deriving precise abundance ratios from spectroscopic data of active comets presents formidable analytical challenges. The complexity of dust clouds, where varying excitation conditions, contamination from multiple emission sources, and fluctuating physical environments can all influence spectral signatures, makes accurate quantification difficult. These factors can easily distort the apparent presence or absence of specific elements, leading to potential misinterpretations. Consequently, what might appear as a deficiency or absence of iron could just as well be a consequence of observational constraints, rather than a true indication of the dust's composition. The anomalies observed in the polarization signatures, those subtle optical fingerprints that seem to set the interstellar object known as 3I Atlas apart from typical solar system comets, can be plausibly explained through natural processes. Variations in dust physics, such as differences in grain size distributions, porosity, or compositional modifications, are sufficient to produce unusual polarization patterns without invoking artificial engineering. Dust particles in interstellar environments are subjected to different processing mechanisms than those experienced by comets within our solar neighborhood. Factors like cosmic ray bombardment, interactions with stellar winds, and repeated thermal cycling during long interstellar journeys can alter the physical and optical properties of dust grains, endowing them with distinctive behaviors and signatures. These processes can generate optical and polarization characteristics that are unlike anything observed in comets formed and evolved solely within our solar system. Such differences are natural consequences of the unique environmental conditions in interstellar space, rather than indications of artificial fabrication. It is also vital to recognize the importance of scientific conservatism in this field. Maintaining cautious skepticism helps safeguard the credibility of astronomical research. Making definitive claims about extraterrestrial technology based on ambiguous or limited data risks undermining public trust and scientific integrity, especially if those claims turn out to be false positives. The scientific community has learned this lesson the hard way. Early announcements suggesting biosignatures in Martian meteorites, which sparked worldwide excitement, were eventually proven to have more mundane explanations upon thorough analysis. The media's tendency to amplify preliminary interpretations further complicates matters, often transforming tentative hypotheses into seemingly established facts and fostering unrealistic expectations of revolutionary discoveries. Such premature assertions can distort public understanding and inflate expectations beyond what the evidence justifies. However, the pushback against these overreaches is not merely about protecting institutional credibility. It also involves rigorous scientific scrutiny. Experts in orbital mechanics, for instance, have demonstrated that the supposed improbability of certain trajectory alignments can, in fact, fall well within the expected range for randomly oriented interstellar paths. Similarly, the chemical anomalies observed, though intriguing, do not necessarily exceed the known diversity of cometary compositions formed around different types of stars and in various stellar environments. While the unusual polarization signatures observed in 3I Atlas are indeed atypical compared to solar system standards, they can be sufficiently explained by dust processing mechanisms active in interstellar space, which differ markedly from those in our local environment. The physical and chemical modifications to dust grains, such as changes in size, porosity, and composition, developed under the influence of cosmic rays, stellar winds, and thermal cycling over long journeys, could produce optical signatures that mimic artificiality without requiring any such explanation. Every so-called artificial signature, upon careful examination by specialists familiar with the relevant physics, admits plausible natural explanations. This does not mean that hypotheses proposing artificial origins lack value. Rather, it underscores the importance of rigorous, comprehensive analysis before drawing extraordinary conclusions. Even theories that ultimately prove incorrect can still significantly contribute to the advancement of scientific knowledge. They serve as catalysts that inspire new observations, foster the development of innovative analytical techniques, and compel scientists to articulate with greater precision what constitutes definitive proof, particularly when it comes to confirming an artificial origin of an interstellar object. The speculative notion of alien technology linked to 3I Atlas has, in particular, spurred a wealth of valuable scientific activity. Researchers have launched comprehensive observational campaigns, refined spectroscopic analysis methods to detect subtle chemical signatures, and improved coordination between terrestrial ground-based telescopes and space-based observatories. These collective efforts yield benefits that extend well beyond the initial hypothesis, regardless of whether it ultimately proves correct. This process exemplifies the scientific community's intrinsic capacity for self-correction. Extraordinary claims, especially those that challenge established understanding, are subjected to rigorous scrutiny through peer review, independent verification, and lively debate among experts. Though such exchanges can sometimes become contentious, they invariably strengthen the integrity of scientific inquiry by filtering out unfounded speculation and elevating genuinely substantiated discoveries. Meanwhile, media coverage tends to emphasize the most natural explanations compatible with current data, while also acknowledging the genuine chemical and physical anomalies that make 3I Atlas a uniquely intriguing object. As the most thoroughly observed interstellar visitor in human history, it offers unprecedented insights into the diversity of materials that form around other stars, broadening our understanding of cosmic chemistry. The most compelling scientific narrative emerging from accumulated observations suggests that 3I Atlas is a chemically unusual yet fundamentally natural comet. Its high concentration of carbon dioxide, early onset of volatile activity, and exotic dust properties reflect formation and evolutionary processes that differ from those seen in our solar system, yet do not necessarily imply artificial intervention. This interpretation aligns perfectly with Occam's razor, providing the simplest explanation that accounts for all confirmed data. It expands our perspective on the diversity of interstellar objects without resorting to unverified hypotheses involving advanced extraterrestrial civilizations. Moreover, it challenges and refines our existing theories of comet formation and evolution, all while remaining firmly rooted in well-established physical principles. As ongoing investigations continue, mainstream science remains committed to drawing conclusions based solely on evidence, while maintaining an openness to genuinely revolutionary discoveries, should compelling new data arise. The bar for extraordinary claims remains appropriately high, safeguarding the integrity of astronomical research and ensuring that the pursuit of knowledge proceeds with rigorous skepticism balanced by scientific curiosity. At this juncture, it is essential to shift our perspective entirely and consider a radically different hypothesis that has begun to attract serious attention from reputable planetary formation theorists. This alternative posits that interstellar objects like 3I Atlas could serve as natural, ready-made agents of planetary seeding across the galaxy, redefining our understanding of how planets and systems might originate. One such innovative idea comes from the renowned astrophysicist Suzanne Falsner at the Max Planck Institute for Radioastronomy. She has proposed a revolutionary mechanism that could fundamentally reshape our concepts of planetary formation. Her hypothesis suggests that these cosmic wanderers are not merely fragments or debris, but active contributors, potentially carrying the raw materials or even the initial seeds necessary to trigger planet formation in young stellar systems throughout the galaxy. Her innovative hypothesis proposes that interstellar objects, wandering bodies like 3I Atlas, might function as natural pre-existing planetary seeds. These objects, she suggests, could be captured by young stellar systems and then rapidly evolve into gas giants through accelerated accretion processes. This idea offers an elegant solution to one of the most long-standing conundrums in planetary formation theory: the timeline problem. In traditional models, the formation of planets is a sluggish affair, requiring millions of years for tiny dust grains within a protoplanetary disk to collide, stick together, and gradually coalesce into larger bodies known as planetesimals. Over time, these planetesimals further accrete material, eventually reaching sizes capable of exerting significant gravitational pull to attract gaseous envelopes from the surrounding disk. But here lies the dilemma. Astronomical observations show that the gaseous disks around young stars tend to dissipate within just a few million years. Far too short a window for such slow, incremental growth to produce the massive planets we observe, especially the gas giants. This stark discrepancy makes the question of how planets, particularly large ones, can form so swiftly a challenging mathematical and physical puzzle. How do these worlds manage to grow large enough in such a brief span to capture their substantial atmospheres before their stellar nurseries vanish? Conventional core accretion theory struggles under this timeline constraint, prompting scientists to seek alternative explanations. Enter Falsner's innovative simulations, which reveal an intriguing correlation. More massive stars seem more effective at capturing interstellar objects through gravitational interactions. Correspondingly, astronomical surveys have identified a higher frequency of giant planets orbiting larger stars, lending circumstantial support to the interstellar seeding hypothesis. The core idea is that in the dense stellar nurseries where young stars are born, clusters containing hundreds or even thousands of sibling stars, gravitational dynamics are complex and chaotic. In such crowded environments, interstellar objects can be exchanged between stellar systems or captured outright from the broader galactic population. A critical factor in this process is the role of gas drag within the protoplanetary disks. When an interstellar object ventures close to a young star, frictional forces between the object and the disk's gaseous material can significantly reduce its velocity. This dissipation of energy increases the likelihood that the object will become gravitationally bound, effectively transforming it from a wandering interloper into a planetary core. Once captured, this core, possibly measuring kilometers across rather than mere meters, possesses an enormously enhanced gravitational cross-section. This means it can more efficiently attract additional material through direct collisions with solids and gravitational focusing of smaller particles. processes that can accelerate growth to substantial sizes within time frames compatible with the dispersal of the protoplanetary disk. This rapid mass accumulation allows the core to reach a size capable of capturing a gaseous envelope swiftly, often within just a few 100,000 years, far faster than traditional models predict. As a result, the planet can attain Jovian masses during a narrow window when the gaseous component of the disk is still present, thus solving the timeline problem. Falzner's framework makes specific testable predictions about planetary system architectures. For instance, planets born from captured cores would carry chemical signatures, distinctive elemental and isotopic compositions, reflecting the environments of their original stellar systems. This chemical fingerprinting could, in principle, be detected, offering a way to trace the origins of gas giants back to interstellar seeds, rather than in situ formation alone. The chemical signatures observed in a select few interstellar objects provide compelling clues supporting the planetary seeding hypothesis. For instance, the confirmed visitors, 1I/Oumuamua, 2I/Borisov, and 3I Atlas, each exhibit a remarkable range of compositions that hint at diverse origins across many stellar environments. The first/Oumuamua showed no detectable signs of volatile activity, suggesting its makeup is primarily composed of refractory non-volatile materials. The second/Borisov closely resembled the typical solar system comet, indicating it likely formed in an environment similar to our own outer planetary regions. The third, 3I Atlas, presents an entirely different profile, characterized by a dominance of carbon dioxide and unusual dust properties. An intriguing diversity that implies these objects sample formation conditions from a broad spectrum of stellar systems. This variety among the small sample of interstellar visitors supports the idea that these objects are not random, but rather represent a collection of material ejected from many different stellar origins, each carrying unique chemical signatures reflective of their birth environments. If these objects indeed serve as carriers of planetary core material, they could help explain the wide range of exoplanet compositions and characteristics that current models find difficult to reproduce solely through local formation processes within our solar system. The timing of the discovery of 3I Atlas offers a rare and valuable opportunity to scrutinize the seeding hypothesis more directly. Unlike earlier interstellar objects detected only after their closest approach to Earth, this object was identified early enough in its journey that detailed compositional and structural analyses could be performed while it remains relatively nearby. This early detection allows us to examine properties that might be ideal for rapidly forming planetary cores, making it a prime candidate for testing the concept that interstellar objects can act as seeds for new planets. Its composition, notably rich in carbon dioxide, suggests that 3I Atlas likely originated in the cold, distant regions of another stellar system, where such volatile compounds could condense into solid form efficiently. The early signs of water activity indicate that the object possesses sufficient porosity and volatile content to facilitate active outgassing, a process that could be crucial during planetary core formation. These volatile-rich interiors may play a vital role in accelerating the growth of planetary seeds, as heating during accretion phases could lead to rapid expansion and increased collision cross-sections, thereby enhancing the efficiency of particle capture. Such properties make these objects not only fascinating cosmic samples but also potentially powerful agents in the rapid assembly of planetary cores across the galaxy. The size of this interstellar object, estimated to range roughly from 0.44 kilometers up to about 5.6 kilometers in diameter, aligns closely with the theoretical predictions for what constitutes an effective planetary seed. Smaller objects, significantly below this scale, likely lack the necessary gravitational influence to quickly gather and accrete material from surrounding protoplanetary disks, thereby limiting their potential to serve as catalysts for planetary formation. Conversely, larger bodies, while possessing greater mass and gravitational reach, are exceedingly rare within the galaxy, making it difficult to reconcile their scarcity with the observed frequency of planets around stars. The hypothesis proposed by Falsners is far more than mere abstract speculation rooted in speculation or mathematical modeling. It offers concrete, testable predictions regarding the properties of planetary systems, the distribution and characteristics of interstellar objects, and the statistical relationships between the nature of stellar clusters and the efficiency with which planets form. These predictions are not merely theoretical constructs, but are actively subject to validation through ongoing as well as future observational campaigns. For example, the European Space Agency's Gaia mission has already begun the meticulous process of identifying potential interstellar visitors by employing ultra-precise astrometric measurements of stellar motion patterns. This innovative approach can reveal anomalies in stellar positions and velocities that suggest the gravitational influence of nearby, fast-moving objects passing through the galaxy. Complementing this, the upcoming Vera Rubin Observatory's Legacy Survey of the Sky, an ambitious project designed to image the entire night sky repeatedly over many years, promises to dramatically expand our census of transient phenomena. This survey is expected to uncover many additional interstellar objects presently unknown, vastly enriching our understanding of the population and diversity of these wandering celestial bodies. In addition, the James Webb Space Telescope's capabilities in observing protoplanetary disks, those swirling regions of dust and gas around young stars, could prove instrumental in testing the seeding hypothesis. By detecting specific chemical signatures within these disks, such as isotopic ratios, elemental abundances, and volatile inventories that match those expected from captured interstellar material, scientists could gather circumstantial evidence supporting the idea that planetary building blocks are sometimes formed or influenced by material originating from outside the local stellar environment. Furthermore, the seeding hypothesis extends beyond individual object studies, linking to broader questions about the chemical evolution of the galaxy itself. If interstellar seeding operates with sufficient efficiency, then the chemical and isotopic makeup of planetary systems would no longer be viewed as isolated, localized phenomena, but as elements of a vast interconnected network of material exchange. Stellar nurseries, those stellar birthplaces, would function as galactic-scale mixing chambers where materials ejected from countless stars, whether through winds, supernova, or planetary ejections, becomes redistributed among developing planetary systems. This process would naturally lead to a chemical diversity in planets and atmospheres that surpasses what could be generated solely through local processes, potentially explaining the wide range of compositions observed across exoplanets. This galactic perspective fundamentally transforms our understanding of planetary formation from a process confined within individual systems to a collaborative, galaxy-wide enterprise involving the exchange and redistribution of matter across interstellar distances. The implications are profound, reaching beyond the technical mechanics of how planets form to touch on the very nature of cosmic connectivity and the shared heritage of planetary systems throughout the galaxy. Viewing the object known as 3I Atlas through this lens, it assumes a role far greater than that of an unusual comet or a potential artificial probe. Instead, it becomes a messenger, carrying within it chemical memories from remote stellar environments, an interstellar courier of raw materials that might have played a part in seeding planetary formation across the galaxy. While it remains uncertain whether this particular object ever served such a function, as it appears destined to leave our solar system rather than becoming part of our planetary family, its composition and physical structure still offer critical insights. These insights deepen our understanding of the types of materials available for cosmic seeding processes operating throughout galactic history. The seeding hypothesis itself provides a natural explanation for the rapid formation of planets, one that does not require invoking exotic physics or the intervention of extraterrestrial intelligence. Instead, it suggests that the galaxy functions as a vast, ongoing recycling system, an interconnected network where materials are exchanged, accumulated, and used to accelerate planetary growth, thus making the emergence of planets a more dynamic and widespread phenomenon than previously thought. The galaxy can be envisioned as an immense, interconnected recycling network, an intricate cosmic system that continually redistributes materials across vast interstellar distances. This process not only facilitates the rapid growth of planetary bodies through gravitational capture and accretion, but also hints at a universe far more dynamic and interconnected than previously imagined. Yet even this elegant concept of natural seeding raises deeply profound questions about the very origins and widespread distribution of life throughout the history of the cosmos. It compels us to reconsider long-held assumptions about how planets and potential habitats for life come into being. To truly grasp why the idea of interstellar seeding constitutes such a groundbreaking and revolutionary shift in our understanding, we must first revisit the foundational models that have historically shaped planetary formation theories over the past several decades. For a long time, the prevailing scientific framework has divided the formation of giant planets into two primary competing mechanisms, each with its own set of challenges and unresolved issues. The first is the core accretion model. This theory suggests that within the protoplanetary disks surrounding young stars, tiny dust grains gradually collide and stick together, primarily through electrostatic forces. Over time, these particles coalesce into larger and larger bodies, eventually forming planetary cores. However, this process encounters the notorious meter-size barrier. At this critical size, aerodynamic drag, the force exerted by the gas in the disk, becomes so significant that these growing objects tend to spiral inward and be swallowed by their parent star before they can reach the mass needed for gravitationally capturing substantial gaseous envelopes. This fundamental timeline problem has long challenged the viability of pure core accretion, prompting scientists to search for solutions. One such solution emerged with the discovery of pebble accretion. Unlike earlier models relying solely on random collisions, pebble accretion involves gravitational focusing effects, allowing planetesimals, building blocks of planets, to more efficiently sweep up streams of smaller particles, or pebbles, passing through their vicinity. This mechanism accelerates growth, potentially shortening the timeline from millions to just a few thousand years, for forming sufficiently massive cores capable of gas accretion. Nevertheless, even pebble accretion requires several million years to produce planetary cores large enough to enable significant gas capture, still challenging the observed rapid formation timescales. The second mechanism, gravitational disk instability, offers an alternative pathway. This model posits that dense, massive regions within the protoplanetary disk can directly collapse under their own gravity, forming giant planets swiftly, potentially within thousands of years, bypassing the slow accumulation process. However, this process demands very specific conditions. The disk must be sufficiently massive, cool enough to allow gravitational instabilities to develop, and possess the right physical properties. Such conditions may not be common around most young stars, raising questions about the universality of this pathway. Compounding these theoretical challenges are the stringent observational constraints. Measurements of protoplanetary disks around young stars often reveal masses that appear insufficient to support either core accretion or gravitational instability in their current states. Furthermore, the observed lifespans of gas-rich disks, usually only 1 to 10 million years, impose tight timelines that leave little room for the slow processes envisioned by traditional theories. This is especially true for more massive stars, which tend to disperse their disks more rapidly through intense stellar winds and radiation, seemingly leaving inadequate time for giant planet formation. Paradoxically, surveys demonstrate that these more massive stars actually host giant planets more frequently than their lower mass counterparts, an observation directly at odds with what conventional models would predict. This apparent contradiction leads us to a tantalizing yet entirely speculative question. Could external seeding, perhaps via interstellar objects, have played a role in planetary formation within our own solar system some 4.6 billion years ago? While such ideas remain within the realm of conjecture, circumstantial evidence hints that in the early galaxy, the influx rates of interstellar objects might have been significantly higher. During that primordial epoch, densely packed stellar nurseries and turbulent galactic conditions could have facilitated a far more frequent exchange of material between stellar systems, potentially seeding nascent planets with the raw ingredients or even core structures necessary for rapid growth. Although direct proof remains elusive, this possibility opens an intriguing avenue, suggesting that the formative processes of planets might have been influenced or even accelerated by a cosmic exchange of matter during the galaxy's distant past. Our solar system originated within a bustling stellar nursery, an expansive cloud of gas and dust from which hundreds or even thousands of sibling stars were born simultaneously, all coalescing from the same colossal molecular cloud. Within this densely packed environment, gravitational interactions and close stellar encounters would have been commonplace, creating a dynamic playground where planetary systems could exchange material through interstellar object exchanges. Such a setting would have fostered a complex web of interactions, enabling the transfer of matter across different star systems over millions or billions of years. Moreover, the interstellar object known as 3I Atlas may originate from the galaxy's thick disk population, a component of the Milky Way that formed during earlier epochs when the galaxy's chemical composition and stellar density profiles differed significantly from those of the present day. If this connection is confirmed, it suggests that wanderers like 3I Atlas could carry chemical memories spanning billions of years of galactic evolution. These ancient origins open fascinating possibilities. That interstellar objects are not merely random debris but carriers of a long interconnected history, embodying a form of cosmic recycling that operates over geological timescales. Over billions of years, materials ejected from planetary systems, whether through planetary collisions, stellar winds, or other dynamic processes, could have traveled vast interstellar distances only to be later incorporated into the formation of new systems. Such a continual cycle would weave a vast, intricate network of chemical inheritance, linking stellar environments across the galaxy's history. This perspective fundamentally shifts our understanding of planetary system formation from isolated, independent events into parts of a grand, interconnected process, one in which materials and their evolutionary stories are shared across cosmic scales, creating a galactic tapestry of chemical and physical continuity. In this cosmic context, even giants like Jupiter and Saturn might harbor traces of material originally forged around stars that had long since died, stars that predate our Sun by hundreds of millions or even billions of years. The composition and activity patterns observed in interstellar visitors such as 2I Borisov and 1I Oumuamua, two objects with contrasting behaviors, provide clues that help interpret these cosmic wanderers. Borisov, with its familiar chemical signature, active outgassing, and dust production, resembles typical solar system comets, suggesting it formed in a familiar outer region environment similar to our own planetary neighborhood. In stark contrast, Oumuamua displayed no detectable outgassing, unusual acceleration patterns and geometric constraints hinting at an elongated or flattened shape unlike the more spherical or irregular forms of standard comets or asteroids. This unusual combination of properties sparked initial speculation that it might be artificial in origin, an idea that continues to echo in discussions of 3I Atlas. Meanwhile, 3I Atlas occupies an intermediate position, showing clear cometary activity through gas and dust emission but with chemical signatures that are markedly different from both typical solar system comets and Borisov. This unique profile makes it especially valuable, as it offers insights into the full spectrum of interstellar object diversity. The chemical variation among this small sample hints at a wide range of formation environments, each sampling different stellar architectures, evolutionary histories, and stages of galactic chemical development. Each interstellar object thus acts as a unique fingerprint, carrying within its composition clues about the conditions around its parent star, enabling researchers to perform retrospective studies of stellar environments light years away. Although estimates of how many such objects populate our galaxy remain highly uncertain, recent theoretical models suggest that our solar system could encounter several interstellar visitors of similar size each year. Most of these tiny travelers pass unnoticed, due to their small size, lack of activity, or unfavorable observation geometries, making their detection a challenge for current technology. The upcoming era, heralded by the Vera Rubin Observatory's Legacy Survey of Space and Time, promises to fundamentally transform our understanding of the dynamic universe, particularly with regard to the population of fleeting interstellar visitors passing through our solar neighborhood. Set to commence operations in the mid-2020s, this groundbreaking facility will systematically scan the entire visible sky at regular intervals, every few nights, comparing successive images to detect moving objects with unprecedented precision. Such a comprehensive and frequent monitoring system is expected to dramatically increase our detection rate of transient objects, including those originating beyond our solar system. Statistical models predict that once the Rubin Observatory reaches its full operational capacity, it could identify hundreds of interstellar objects each year, vastly expanding our current sample size. This surfeit of data will empower scientists to rigorously test theories such as the seeding hypothesis, which posits that interstellar objects might serve as carriers of material, potentially even biological or chemical, between star systems. With a larger and more representative sample, researchers will be able to analyze the characteristics, size distributions, and chemical compositions of these wanderers with far greater confidence, uncovering patterns and diversities that were previously obscured by limited data. Enhanced detection capabilities are also poised to refine our estimates of how frequently such objects are captured by young stellar systems, which has direct implications for the viability of seeding mechanisms. If interstellar objects are significantly more numerous than our current estimates suggest, the volume of raw material available for planetary seeding, whether through natural gravitational capture or other processes, may be substantially greater, potentially accelerating planetary formation and chemical exchange across the galaxy. The seeding hypothesis itself makes specific testable predictions regarding the relationship between the properties of stellar nurseries and the architectures of the resulting planetary systems. In particular, densely populated massive stellar clusters are expected to facilitate higher rates of interstellar object capture, possibly explaining observed correlations between a star's environment and the likelihood of hosting planets. These predictions can be scrutinized through the integration of data from the Gaia spacecraft, which tracks stellar birth cluster associations via precise astrometry, with exoplanet surveys that characterize the properties of planetary systems around stars with well-documented formation histories. By combining these datasets, Scientists can perform statistical analyses to detect potential signatures of seeding processes that may have been active during the formative stages of planetary systems. Such signatures might include specific patterns in planetary compositions, orbital distributions, or system architectures that align with the predicted influence of interstellar material influx. Beyond these immediate scientific objectives, the broader context encompasses profound questions about the history of galactic chemical evolution and the mechanisms behind material redistribution across vast cosmic distances. If the process of seeding has operated efficiently over billions of years, then the chemical fingerprints of planetary systems, such as atmospheric compositions and bulk elemental ratios, may be entangled across large regions of the galaxy, reflecting a history of material exchange that surpasses the limits of local formation processes. This galactic mixing perspective implies that the diversity observed in exoplanet atmospheres and compositions could be significantly broader than what could be produced solely by local in situ chemistry. Instead, the formation regions might have imported components condensed around stars with varying masses, metallicities, and evolutionary paths, enriching planetary building blocks with a mosaic of galactic heritage. In this expansive framework, the interstellar object known as 3I Atlas offers a rare and invaluable opportunity. Although this particular object appears destined to escape our solar system without being captured, its early detection, coupled with detailed observational campaigns and sophisticated analytical techniques, provides critical insights into the nature of materials that may once have participated in seeding processes. Whether or not 3I Atlas ever served as a planetary core, the data gleaned from its composition and physical properties serve as a window into the types of objects that traverse the galaxy, potentially delivering the raw ingredients for planetary development and chemical diversity across cosmic history. This opportunity underscores the importance of studying interstellar wanderers, not just as curiosities but as key witnesses to the galactic exchange of material and perhaps even life itself. The idea of cosmic seeding fundamentally shifts how we perceive interstellar objects, elevating them from mere occasional visitors to potential architects of planetary diversity across our galaxy. Instead of viewing these wanderers as isolated anomalies, this hypothesis suggests they could serve as carriers of complex, preformed materials, elements that influence the makeup and evolution of worlds formed around distant stars. In this context, the case of the 3I Atlas becomes a critical testbed. Its distinctive chemical signature, particularly the remarkable dominance of carbon dioxide, offers the first tangible clue in assessing whether such objects might indeed act as cosmic seeds. This particular chemical fingerprint could trace the origins of the object to environments significantly colder and richer in carbon dioxide than the typical regions where our solar system's comets formed. Such extreme conditions are plausible in the distant outskirts of massive protoplanetary disks, where the temperature drops enough to allow carbon dioxide to condense and remain stable, or around low-mass stars that possess extended snowline boundaries, regions where volatiles like carbon dioxide can freeze out at greater distances from the star. From the perspective of seeding, this composition profile is not necessarily anomalous. Rather, it could confer specific advantages. Since carbon dioxide remains stable at temperatures higher than those at which water ice sublimates, objects enriched with CO2 could sustain volatile-driven activity over a broader range of stellar distances. In practical terms, a seed with a high carbon dioxide content might stay active during the critical phases of capture and initial integration into a planetary system. This is especially relevant because objects dominated by water ice tend to become dormant as they approach the star's warmth, whereas CO2-rich bodies could continue to outgaze and interact dynamically with their environment. Evidence of early hydroxyl activity, an indicator of water vapor dissociation, detected at a distance of about 3.5 astronomical units from the Sun, underscores this possibility. It demonstrates that the 3I Atlas contains substantial water ice, despite its pronounced CO2-rich coma. Such a mixture points to a layered or chemically mixed volatile structure, capable of producing both early water signatures and prolonged carbon dioxide emissions as solar heating penetrates deeper into the object's interior. This layered volatile architecture could be highly beneficial during the process of planetary seed formation. Multiple mechanisms for expansion and particle capture would be enabled by the presence of different volatiles. Initial water outgassing might create an extended tenuous atmosphere around the object, increasing its effective collision cross-section and making it more likely to intercept and accrete disk materials. As it moves closer to the star or during subsequent orbital evolution, sustained carbon dioxide outgassing could prolong this activity over longer timescales and at wider orbital distances. Furthermore, the polarimetric measurements, particularly the unusual dust properties inferred from scattering behavior, add weight to the argument for an exotic formation environment. The observations of an extended negative polarization branch and distinctive scattering patterns suggest that the dust grains within the object's coma possess properties unlike those of familiar solar system comets. These grains may have high porosity, unusual size distributions, or unique compositional features, attributes likely acquired during extended interstellar journeys. Over millions of years, cosmic ray bombardment, stellar wind interactions, and thermal cycling could alter grain structures in ways that are not feasible within a single stellar system's environment. For seeding purposes, such altered dust properties could enhance accretion efficiency. Highly porous, fluffy materials have larger geometric cross-sections relative to their mass, increasing the likelihood of collision and sticking with other particles in the protoplanetary disk. Additionally, the distinctive optical and scattering properties suggest chemical compositions that might be particularly effective catalysts for subsequent grain growth and aggregation. These features, porosity, size distribution, and composition, could all work synergistically to make the object a more effective building block during the assembly of planetary cores. The size constraints derived from high-resolution observations with the Hubble Space Telescope place the diameter of the 3I Atlas at approximately 0.4 to 5.6 kilometers. This size range is significant because it suggests an optimal balance, large enough to exert a meaningful gravitational influence and to serve effectively as a seed, yet small enough to be captured efficiently by the gas and dust in a protoplanetary disk. Such an object could act as a catalyst, accelerating planetary formation processes by providing a pre-assembled, chemically complex core that could rapidly attract surrounding material, thereby bypassing the slow, incremental growth phases that conventional models often struggle to explain within the limited lifespans of protoplanetary disks. In sum, the chemical and physical characteristics observed in the 3I Atlas, its carbon dioxide dominance, layered volatile structure, and exotic dust properties, support the intriguing possibility that interstellar objects could serve as natural or even engineered seeds for planetary systems. They might carry outsized influence in shaping planetary architectures, delivering not just raw materials, but also preformed structures that catalyze rapid planet formation across the galaxy. Such a paradigm challenges conventional theories, expanding our understanding of the origins and diversity of worlds beyond our solar system. The size of the interstellar object, estimated to fall between 4 and 4.4 kilometers, with an upper limit approaching approximately 5.6 kilometers, places it within a potentially optimal range for planetary seeding processes. This intermediate scale is particularly significant because it strikes a delicate balance. Objects of this size are large enough to exert a meaningful gravitational influence, increasing the likelihood of effective capture during encounters with young stellar systems. At the same time, their relatively modest dimensions mean they can be efficiently slowed down and retained through interactions with the gas and dust in protoplanetary disks via gas drag mechanisms. In contrast, objects much smaller than this range, say below a few kilometers, may lack the necessary mass to rapidly accrete material from the disk or to influence planetary formation processes significantly. Their limited gravitational pull would make sustained capture or incorporation into forming planetary bodies less probable. Conversely, bodies substantially larger, perhaps exceeding 10 kilometers, would pose their own challenges. Their heft could render gravitational capture exceedingly difficult unless the encounter geometry is extraordinarily precise, involving specific angles and velocities that facilitate gravitational binding within the dynamic environment of a young stellar system. Such massive objects might require conditions that are statistically rare, reducing the likelihood of their effective participation in seeding mechanisms. This intermediate size window, therefore, appears to be a sweet spot, large enough to serve as effective seed nuclei for planetary growth, but small enough to be readily captured and integrated into nascent planetary systems. Theoretical models support this idea, suggesting that objects within this size bracket could be produced relatively abundantly. These formations might originate from collisional grinding of larger bodies, where larger planetesimals collide and fragment into smaller, more numerous objects, or through direct condensation in the colder outer regions of protoplanetary disks, where materials cool sufficiently to solidify into sizable bodies. Further clues about the origins of 3I Atlas point toward a possible formation within the galaxy's thick disk, a component of the galaxy characterized by stars and objects that formed during earlier epochs of galactic evolution, potentially billions of years ago. Kinematic analyses which study the object's motion indicate that it may have originated in this older, more metal-poor region, where stellar densities and chemical processing mechanisms differed markedly from those prevalent in the more recent thin disk. If this connection is confirmed, it would suggest that 3I Atlas carries within it a chemical and isotopic record, an archival snapshot of conditions that existed long before our solar system's formation. Such a heritage implies that the isotopic ratios, elemental abundances, and molecular inventories preserved within its nucleus could sample environments from the earliest periods of stellar formation, even from stars that completed their life cycles long before our sun ignited. This transforms 3I Atlas from merely a contemporary interstellar visitor into an ancient relic, an archaeological sample, offering insights into the chemical makeup of the galaxy during its formative years. Its materials might include components originally formed around stars that had already gone through their entire life cycles, enriching the galaxy's chemical diversity long before the emergence of our planetary system. The detection of cyanogen, a molecule composed of carbon and nitrogen, further enhances its significance in the context of planetary seeding. Cyanogen emissions, which are typically associated with the sublimation of organic compounds, suggest that 3I Atlas carries within it complex organic molecules that could serve as precursors to life. The presence of such prebiotic molecular building blocks alongside its unusual mixture of volatile substances bolsters the idea that objects like this could deliver essential ingredients for the emergence of life directly into developing planetary environments. This organic inventory might accelerate prebiotic chemistry, fostering the conditions necessary for life to begin on planets formed from material that originated in distant, chemically rich stellar nurseries. In addition to its organic components, 3I Atlas shows signs from spectroscopic analysis, specifically nickel emission lines, that point to a composition containing refractory or heat-resistant elements. While these nickel signals do not necessarily imply industrial processing or artificial origin, They demonstrate that the object contains solid, non-volatile materials alongside its gases and ices. This mixture of volatile compounds and refractory metals is particularly advantageous for seeding mechanisms, as it provides both the volatile drivers necessary for active outgassing, an essential process for dispersing material into planetary atmospheres and surfaces, and the solid materials capable of forming substantial planetary cores. Together, these characteristics, its size, chemical complexity, and mixed composition, highlight the potential of 3I Atlas as a versatile seed. Its volatile components can fuel active outgassing, aiding in the dispersal of organic molecules and other materials, while its refractory elements serve as the foundational building blocks for planetary cores. This combination makes it an especially promising candidate for the role of a cosmic seed, an object capable of delivering both the ingredients and the physical framework necessary to kickstart planetary development and perhaps even foster the emergence of life. The presence of volatile compounds within 3I Atlas plays a crucial role in facilitating swift expansion and boosting the efficiency of particle collection during the early stages of its formation. These volatile elements act like cosmic catalysts, enabling the object to rapidly develop a gaseous envelope that can trap and accrete surrounding dust and particles more effectively. On the other hand, refractory materials, those with high melting points, serve as the sturdy, solid backbone necessary for the ongoing gravitational accumulation of matter, ultimately guiding the growth toward planetary-scale masses. Spectroscopic investigations have uncovered a remarkable level of chemical intricacy within 3I Atlas, revealing multiple emission lines that span a broad spectrum of molecular and atomic species. This diversity of chemical signatures suggests that the object likely originated in an environment capable of preserving a wide array of materials, rather than one that has undergone intense processing or homogenization, which might be expected if the object had formed solely within a local, highly evolved planetary system. The fact that such chemical variety has been maintained throughout its interstellar voyage strongly indicates that minimal thermal alteration occurred during its passage through the galaxy. This observation supports the idea that complex chemical compositions can be transported across vast interstellar distances without substantial molecular breakdown, despite the harsh conditions of cosmic ray bombardment or occasional stellar encounters that could otherwise fragment or alter delicate molecules. Current observational data demonstrate that 3I Atlas exhibits multiple characteristics consistent with being an effective cosmic seed material. Its size falls within a range suitable for gravitational capture, and it possesses a complex chemical inventory that includes both volatile and refractory components, an indication of a rich and diverse formation environment. However, directly testing whether 3I Atlas could have played a role in seeding planetary systems remains impossible at this stage, mainly because the object is currently on a trajectory that will carry it out of our solar system, preventing any chance of long-term gravitational capture. The dynamics of such encounters, particularly the specific geometries needed for successful seeding, require that the object pass through a young stellar system with a sufficiently massive protoplanetary disk. Presently, 3I Atlas is following a hyperbolic trajectory that will see it depart from the solar neighborhood after its passage, effectively making it a fleeting visitor. Interestingly, this escape trajectory offers a valuable scientific advantage. It allows us to study the object's composition and structure in detail, without the complications that come with permanent gravitational capture, such as prolonged interaction with the host star or planetary bodies. While 3I Atlas remains accessible to our observational instruments, it serves as a representative sample for understanding the characteristics of potential seeding materials. Ongoing spectroscopic analyses conducted through multiple telescopes are working to establish detailed chemical fingerprints that will serve as benchmarks. These benchmarks will be critical in identifying similar materials in future interstellar objects or even within exoplanetary systems. By comparing the isotopic ratios, elemental abundances, and molecular inventories measured during this campaign, scientists aim to create a reference profile, an interpretive standard, that can be used to distinguish materials that originated as cosmic seeds from those that formed locally within planetary systems. This approach of building a detailed chemical library offers the potential for retrospective identification of seeding signatures in mature planetary systems. Even if this particular object did not participate directly in planetary formation, its chemical makeup provides invaluable insights into the raw materials available for cosmic seeding throughout the galaxy's history. In essence, 3I Atlas acts as a probe into the primordial building blocks that may have contributed to planetary and possibly even biological development across cosmic time, offering a window into the materials and processes that have shaped the evolution of worlds beyond our solar system. The tentative yet promising conclusion regarding 3I Atlas as a potential seed material remains open, but it is undeniably encouraging. This interstellar object displays numerous traits that align with what we might expect from an effective planetary seed. Characteristics related to its composition, structural integrity, and physical properties, while also offering us an unprecedented opportunity for meticulous analysis. Such detailed scrutiny could unlock insights into the fundamental nature of interstellar objects and their roles within our galaxy. But this leads us to a profound and far-reaching question. If these cosmic seeds regularly traverse the vast expanses between stellar systems, carrying intricate chemical recipes and a multitude of materials, could they also be vehicles for the most complex chemical processes known to science? The molecular building blocks of life itself? This thought, once purely speculative, now warrants serious contemplation given the accumulating evidence and the remarkable nature of these celestial visitors. Expanding our view beyond individual objects, the broader implications of this phenomenon fundamentally challenge and reshape our understanding of how matter moves and exchanges within the galaxy. Instead of considering stellar systems as isolated islands of chemistry, we can now envision them as interconnected nodes within a colossal galactic network. In this framework, interstellar objects, these tiny travelers, act as cosmic couriers, ferrying organics, minerals, and other fundamental compounds along gravitational pathways that stretch across entire light years and eons of cosmic time. This galactic cross-pollination operates on timescales that are incomprehensibly vast compared to human lifespans. Yet in the grander scheme of the galaxy's evolution, these exchanges happen so frequently that they could be nearly continuous. A single interstellar traveler might, during its million-year voyage, pass through or near dozens of different stellar systems, each encounter representing a potential opportunity for capturing, delivering, or exchanging chemical cargo. These interactions could have accumulated over countless journeys, creating a dynamic, interconnected web of material transfer that spans the galaxy. The implications of this process are staggering when scaled up to the entire galactic population. Our Milky Way galaxy is estimated to contain approximately 400 billion stars, most of which likely hosted their own protoplanetary disks during their formative years. If even a minuscule fraction of these systems engaged in material exchange through interstellar objects, whether by capturing these travelers or by shedding material into the galactic medium, the result would be a galaxy-wide mixing of chemical ingredients on a scale previously unimaginable. Such a mechanism could facilitate the widespread distribution of complex organic molecules, prebiotic ingredients, or even primitive life forms, effectively creating a galactic soup of life's foundational components. This perspective naturally connects to the long-standing hypothesis of panspermia, the idea that life or its ingredients can be transported across cosmic distances, seeding worlds and perhaps spreading life itself. Traditionally, panspermia envisions rocks ejected from planetary surfaces, impact ejecta, carrying dormant microbes or organic compounds to other planets or moons. Interstellar objects refine and elevate this concept by proposing a more elegant, purpose-built mechanism. Objects that are naturally optimized for interstellar survival and chemical preservation. Unlike impact ejecta, which originate from planetary surfaces and are subjected to intense heating and shock, these interstellar travelers might sample the deeper, more primitive layers of their parent systems containing material that has experienced minimal alteration since its formation. Such pristine chemical inventories are crucial because they could contain complex organic molecules, isotopic signatures indicative of specific stellar environments, and perhaps even biological materials that have survived the journey across space. The question of whether these materials can withstand the harsh conditions of interstellar travel, particularly cosmic ray bombardment, remains central to evaluating the feasibility of panspermia on a galactic scale. Fortunately, recent theoretical research suggests that several meters of ice and dust, readily achievable within objects like 3I Atlas, could serve as effective shields against cosmic radiation. This shielding could significantly lower exposure levels, preserving the complex chemistry and potential biological components inside these travelers. Advanced models now incorporate the protective effects of magnetic fields generated within such objects, further refining estimates of their survivability over millions of years and across vast interstellar distances. These findings open the intriguing possibility that the molecular foundations of life, or even microscopic life forms themselves, might be transported intact through the galaxy, riding these cosmic vessels. The implications are profound. The galaxy could be a vast, interconnected web of life's building blocks, with interstellar objects acting as natural carriers in a cosmic cycle of chemical and biological exchange. Advancements in our understanding of cosmic materials have brought to light intriguing possibilities regarding the preservation of complex organic compounds during interstellar journeys. The interplay of conducting materials within these objects, combined with potential chemical repair mechanisms, capable of functioning even at extremely low temperatures, offers a glimmer of hope that delicate organic molecules might endure the harsh conditions of deep space. Additionally, the statistical distribution of cosmic ray exposure across the interior of such objects suggests the formation of radiation shadows, regions shielded from energetic particle bombardment, further aiding in the preservation of fragile chemical signatures. While these findings inspire cautious optimism about the survival of complex organic chemistry over vast interstellar distances, the notion that entire living organisms could persist remains highly speculative. It is more plausible, at least with current knowledge, that what is delivered are the fundamental building blocks of life, prebiotic molecules capable of kickstarting biological processes elsewhere, rather than fully formed, functioning biological systems. Looking ahead, statistical models predicated on improved understanding of interstellar object populations imply that encounters with our solar system are far more frequent than the mere 3 confirmed detections suggest. The reality is that most visitors likely go unnoticed, their small sizes, inactive states, or trajectories' unfavorable alignment with our observation capabilities rendering them effectively invisible to current detection methods. However, the upcoming census conducted by the Vera Rubin Observatory is poised to dramatically transform our observational reach. With its unprecedented sky survey capabilities, it is expected to identify hundreds of interstellar visitors each year. This surge in data will provide a robust statistical framework for testing hypotheses related to cosmic seeding processes while offering a wealth of opportunities to analyze the diverse chemical compositions and structural features of these objects. If Rubin's projections hold true, the implications are profound. The supply of raw materials for seeding mechanisms, whether natural or artificially engineered, would be virtually limitless across cosmic timescales. Instead of rare anomalies, young stellar systems would routinely encounter potential seed materials, making the capture and incorporation of such objects into planetary formation processes an inevitable and integral part of galactic evolution. The remarkable chemical diversity observed among our current small sample of interstellar objects, namely Oumuamua, Borisov, and Atlas, hints at a broad sampling of materials originating from a variety of stellar formation environments, evolutionary histories, and galactic chemical epochs. This diversity suggests that the processes responsible for seeding planetary systems could import a wide array of chemical signatures, spanning the entire spectrum of galactic metallicity evolution, stellar mass distributions, and planetary architecture. The implications of such mixing are significant. They point to the possibility that planetary compositions resulting from these imported materials could surpass what local formation processes alone might produce. For example, Oumuamua's apparent lack of volatile activity combined with its unusual geometric constraints hints at an origin in environments rich in refractory materials, substances resistant to sublimation and thermal alteration. In contrast, Borisov's close resemblance to familiar solar system comets suggests it formed under conditions similar to our outer planetary regions, where volatile rich ices dominate. Meanwhile, Atlas exhibits a distinctly different chemical profile, characterized by the dominance of carbon dioxide and unusual dust properties, indicating that different stellar systems contribute unique chemical signatures to the interstellar object population. This spectrum of compositions underscores the notion that massive stars, with their extensive protoplanetary disks, may eject carbon-rich materials into the galaxy, while lower-mass stars could contribute compositions dominated by water ices, formed within their cooler, more distant snowline regions. Such variability in material contributions from diverse stellar types not only enriches the chemical landscape of interstellar objects, but also enhances the potential for these materials to seed planetary systems with a vast array of chemical ingredients, fostering chemical diversity on a galactic scale. The temporal dimension introduces an additional layer of intricacy into the ongoing process of cosmic chemical mixing. Consider objects like 3 Atlas, which might originate from the galaxy's thick disk population. Ancient stellar groups formed billions of years ago. Such interstellar travelers could carry within them chemical memories of bygone galactic epochs, effectively acting as relics that sample the conditions of stellar formation environments no longer present in the modern galaxy. This perspective transforms interstellar objects into cosmic archaeologists, time capsules that preserve and transmit the chemical signatures of ancient galactic chemistry. Their isotopic ratios, elemental abundances, and molecular inventories could offer unprecedented insights into the evolutionary history of the galaxy's chemical landscape, information that remains beyond the reach of traditional astronomical observations. The idea of these objects as vectors for life's building blocks, though highly speculative, warrants serious consideration given the profound implications involved. If interstellar objects routinely ferry prebiotic molecules between different stellar systems, then the emergence of life might be far more probable than estimates based solely on local in situ chemical evolution would suggest. This scenario envisions a vast galactic-scale network, a sprawling mycelial web, through which complex molecules are accumulated, transformed, and propagated across immense distances. In this interconnected system, individual stellar systems become nodes within a broader chemical highway, where molecules can travel via interstellar objects, gradually spreading the ingredients necessary for life. Such a collective distributed form of prebiotic chemistry could surpass the evolutionary potential of any single system acting in isolation, fostering a galactic environment where life's foundational molecules are shared and recycled across cosmic scales. Yet the survival of these fragile molecules over the vast and hostile journey between stars remains an enormous challenge. Radiation damage, extreme temperature fluctuations, and chemical decomposition processes pose significant threats, potentially destroying complex organic compounds long before they reach a suitable planetary or stellar target. The more conservative and perhaps more plausible scenario involves the transport of simpler organic precursors, basic molecules such as amino acids, nucleobases, or simple hydrocarbons, rather than fully formed biomolecules or living organisms. Even this restrained version of the hypothesis would mark a revolutionary shift in our understanding. It would mean that the fundamental chemical ingredients for life are not unique to individual planets or systems, but are instead distributed across the galaxy, waiting to be assembled into living systems wherever conditions permit. Recent breakthroughs in the field of extremophile biology have expanded our conception of life's resilience, revealing organisms capable of enduring conditions once deemed impossible. Certain bacteria, for example, can withstand radiation doses thousands of times higher than previously estimated limits. Others can remain viable for decades in the vacuum of space or survive at temperatures approaching absolute zero. These discoveries broaden the parameter space for potential biological survival during interstellar transit, suggesting that life, if it exists in some form, may be more adaptable and capable of enduring the rigors of cosmic journeys than once thought. Nonetheless, the combination of multiple extreme conditions, the intense radiation, prolonged vacuum, and thermal cycling, over millions of years still represents an extraordinary challenge, even for the most resilient known organisms. The implications of confirmed cosmic seeding, whether by natural processes or through deliberate artificial intervention, reach far beyond the technicalities of planetary formation. If worlds across the galaxy share a common chemical heritage, connected through the exchange of material via interstellar objects, the boundaries separating local and foreign chemistry become essentially meaningless. This interconnected perspective suggests a universe where the very ingredients of life are part of a shared galactic commons, continuously recycled and redistributed through vast cosmic networks. Such a paradigm fundamentally redefines our understanding of planetary and biological evolution, hinting at a universe where life's building blocks are not isolated phenomena but parts of an ongoing galaxy-wide chemical symphony. This expansive galactic perspective suggests that Earth's delicate biosphere may not be entirely isolated but could, in fact, be a divine mosaic woven from materials originally forged around countless stars across billions of years of cosmic evolution. In this view, our planet transforms from a solitary cradle of life into a vibrant participant in a vast galactic network of chemical exchange and biological potential. Each world, including Earth, becomes a collaborative creation, a mosaic pieced together from the elemental contributions of the entire galaxy. When we examine the enigmatic object known as 3 Atlas through this cosmic lens, it takes on a significance far more profound than merely being an unusual comet or a potential artificial probe. Instead, it emerges as a messenger, carrying within its structure chemical memories and traces from distant stellar environments that have, over cosmic history, participated in the grand process of seeding planets with the ingredients of life. It becomes a silent archivist of galactic chemical exchanges, a sample carrying the potential for the transfer of not only molecules, but perhaps even biological systems themselves. Whether this particular interstellar visitor ever successfully delivered its complex cargo into a young, receptive planetary system remains an unresolved mystery. Still, the composition and structure of 3 Atlas provide unprecedented insights into the vast array of materials that could be available for cross-pollination across the galaxy's evolutionary timeline. These materials carried by wandering objects like this might have seeded worlds with the foundational ingredients for life, contributing to the rich diversity of planetary environments we observe today. This raises a tantalizing question. Could some of these cosmic seeds carry more than just chemical compounds? Might they transport actual biological entities, dormant microorganisms or prebiotic systems, designed perhaps by natural processes or even engineered by intelligent civilizations, to create the conditions necessary for planetary life to emerge? Part 10 of this exploration ventures into the provocative alive planet seed concept, a synthesis of 2 radical ideas: that interstellar objects serve as planetary seeds, and that they might harbor life within their seemingly inert forms. This scenario, while highly speculative, is undeniably fascinating and pushes the boundaries of conventional understanding to the very edges of imagination. Imagine that 3 Atlas is not merely a passive delivery system of chemicals but a living spacecraft, an intricate biological vessel crafted to fundamentally influence planetary formation. In this scenario, the object could contain dormant microorganisms embedded within a resilient carbon dioxide-rich matrix. This matrix would serve a dual purpose, protecting these microscopic passengers from the harsh conditions of interstellar space and nourishing them during their long voyage. The dominance of carbon dioxide within 3 Atlas might have multiple biological functions. Not only would CO2 act as an effective radiation shield, its stable, inert nature providing a barrier against cosmic rays and intense radiation, but it could also serve as a vital nutrient source. Autotrophic organisms, those capable of fixing atmospheric carbon, might inhabit this matrix, capable of converting the inert gases into complex organic molecules when conditions are suitable. During the object's close encounters with stars, interior heating caused by the increased proximity could create transient zones of liquid water within the porous matrix. These brief, oasis-like environments could awaken the dormant microorganisms, providing conditions necessary for rapid reproduction, metabolic activity, and dispersal of biological materials into the surrounding environment. Such an awakening would allow these microbial passengers to multiply and potentially influence the chemical and biological evolution of the planetary body they encounter. This speculative biology would need to demonstrate extraordinary resilience, far beyond that of any known terrestrial organism, resistance to the relentless doses of cosmic radiation accumulated over eons, survival in the vacuum of space, tolerance to extreme temperature fluctuations, and the capacity to remain viable in a state of cryptobiosis for millions of years would be essential traits. Only organisms with such advanced resilience could endure the long, perilous journey through interstellar space and remain ready to activate when favorable conditions arise. Recent groundbreaking discoveries of organisms thriving in extreme environments on Earth have invigorated scientific discussions about the vast potential of life's resilience. These extremophile microbes, such as Dina-coxy-radiodurans, can withstand radiation levels thousands of times higher than the doses lethal to most known life forms, suggesting that biological survival might not be as limited as previously believed. Similarly, tardigrades, those tiny resilient creatures, can endure the vacuum of space, extreme temperatures, and decades of complete dehydration, only to spring back to life when rehydrated. Such remarkable feats of resilience underscore that the realm of biological possibility might extend far beyond traditional expectations, opening the door to contemplating life's tenacity in extraterrestrial settings or even within artificial objects drifting through space. Venturing into even more speculative territory, some theorists propose the existence of engineered probes, advanced artifacts deliberately designed to manipulate the material in protoplanetary disks through controlled outgassing. Rather than simply acting as passive seed objects awaiting capture by a star system's gravity, these hypothetical probes might actively participate in the complex process of terraforming entire stellar environments. For instance, the sunward dust plume observed emanating from the interstellar object known as 3I Atlas could, in this scenario, represent a deliberate act of material injection into our solar system's space environment, perhaps intended to influence planetary formation processes or to prepare a system for future colonization. If such objects contain programmable matter or systems capable of self-modification, their outgassing behavior might follow intricate algorithms rather than mere natural sublimation driven solely by solar heating. These algorithms could be designed to achieve specific chemical or physical goals, such as altering the composition of surrounding material, modulating the environment to favor certain elements, or even communicating with other systems or observers. To accomplish such tasks across millions of years and under the unpredictable conditions of diverse stellar encounters, the technology embedded within these probes would need to operate autonomously, adaptively, and with extraordinary precision. The engineering challenges of creating such self-sustaining, highly autonomous systems appear nearly insurmountable with any current or foreseeable technology. Yet from a purely theoretical standpoint, they remain within the realm of possibility for civilizations far more advanced than ours. If such technology exists, observable signatures that could distinguish these engineered scenarios from natural phenomena might include highly repeatable jet or outgassing patterns that align more with programmed objectives than with the random physics of sublimation. Additionally, deviations from the expected physics of natural cometary activity, such as course corrections inconsistent with natural outgassing physics, might indicate active attitude control systems. The detection of narrowband emissions at specific frequencies could serve as telltale signs of communication or energy sources designed for technology rather than physics. Currently, however, observations of 3I Atlas reveal behavior that aligns remarkably well with natural comet physics, exhibiting outgassing patterns that correlate predictably with the object's rotation and proximity to the Sun, without any clear signs of artificial control or engineered signals. The object's activity appears consistent with sublimation processes driven by solar heating, with dust and gas emissions matching established models. This lack of definitive technological signatures does not entirely dismiss the possibility of an artificial origin, but does require the adoption of increasingly sophisticated explanations. It suggests that if the object were an artifact, its creators might have designed it to remain perfectly camouflaged, executing complex objectives through processes that mimic natural phenomena so convincingly that distinguishing between the two becomes exceedingly difficult. An intriguing aspect of this debate involves the question of why now, the timing of the object's activity and apparent reveal. If 3I Atlas is indeed a deliberate reconnaissance device or a terraforming probe dispatched by an advanced civilization, one might ask why it chose this particular epoch of human technological development to make its presence known. Abraham Loeb, a prominent astrophysicist, offers an interpretation suggesting that the perihelion passage behind the Sun might serve as a strategic moment to reduce the chances of detection from Earth-based telescopes. By passing behind the Sun, the object could minimize observational opportunities, thereby maintaining operational security for whatever sensitive activities or purposes it might serve. This timing would allow the probe to carry out its mission while remaining hidden from human detection, at least until it recedes from the Sun's obscuring glare. Such a reasoning underscores the notion that if an artificial origin is correct, the object's actions might be carefully calibrated for concealment, exploiting natural celestial alignments to maximize operational security. Nevertheless, this line of reasoning presumes that hypothetical extraterrestrial civilizations possess an intricate understanding of human observational techniques, yet remain unaware of our comprehensive space-based astronomical infrastructure. Such an assumption raises profound philosophical questions, especially when considering scenarios where an object like a confirmed alive planet seed fundamentally redefines our cosmic perspective and responsibilities. If the galaxy functions as an immense cosmic gardening system, where intelligent seeds actively influence planetary formation, then humanity might not be the product of mere chance or natural evolution, but rather a result of deliberate cultivation. This perspective invites us to reflect deeply on notions of autonomy, purpose, and ethical obligation. Would we, as a species, carry responsibilities to continue or even participate in this galactic cultivation? Should we seek to establish contact with these cosmic gardeners, assuming their existence? And how would such a revelation, if it confirmed that our universe is a curated or seeded environment, reshape our cultural and religious frameworks, which often rest on the premise of cosmic solitude or randomness? The implications grow even more complex if these seeding processes operate through biological mechanisms, dispersing living organisms or prebiotic materials, rather than purely technological means. Such natural panspermia would suggest that life across the galaxy shares a common ancestry, thereby making all biological entities part of a vast, interconnected family, separated by space and time, yet fundamentally linked through shared origins rather than insurmountable evolutionary divides. On the other hand, artificial seeding scenarios raise crucial questions about the intentions and capabilities of these hypothetical cosmic architects. If these benevolent entities aim to maximize the distribution of life, their actions could imply a form of purposeful stewardship, prompting us to reconsider our relationship with potential alien civilizations. Conversely, if their actions are driven by surveillance, manipulation, or even exploitation, the ethical dimensions become far more troubling, demanding careful reflection on humanity's future interactions with such entities. Currently, the available observational evidence offers no support for extraordinary biological or technological interpretations of objects like 3I Atlas. While the object displays chemical and physical anomalies that spark scientific curiosity, these features remain consistent with natural formation and evolutionary processes. Nonetheless, these speculative scenarios are valuable. They serve to broaden our conceptual horizons, inspiring the development of more advanced detection techniques capable of identifying genuine biological or technological signatures should they exist elsewhere or in future discoveries. It remains essential to uphold the scientific principle that claims involving biological or technological origins require extraordinary proof, reproducible, unambiguous evidence, rather than reliance on tentative or ambiguous observations. Such rigor ensures the integrity of scientific inquiry. Yet beyond immediate empirical validation, exploring these possibilities holds immense philosophical significance. They compel us to question foundational assumptions about the distribution of life in the universe, the role of intelligence in planetary and cosmic evolution, and humanity's place within potentially vast, interconnected networks of biological or technological activity. This concept of the alive planet seed highlights the deeply interconnected nature of cosmic processes, an intricate web that might operate across scales ranging from the microscopic to the galactic. It suggests that the universe may be a dynamic, integrated system where molecular interactions, planetary formation, and even the evolution of intelligence are parts of a grand, interwoven cosmic tapestry, one that challenges our current understanding and invites us to reimagine our cosmic role. If life's role in planetary formation, whether through natural processes or deliberate intervention, blurs the traditional distinctions between geology, biology, and technology, then our understanding of the cosmos must evolve accordingly. the enigmatic object known as 3I Atlas, regardless of whether it ultimately proves to be a product of biological activity or an engineered artifact, has already begun to broaden human horizons. It challenges us to reconsider what is possible within the universe's vast tapestry of phenomena, many of which might initially seem mundane or unremarkable. The very process of investigating such a mysterious visitor exemplifies the scientific method at its best. It demonstrates our capacity to seriously entertain radical hypotheses while upholding rigorous standards of evidence assessment. Even hypotheses that turn out to be incorrect serve a valuable purpose. They sharpen our understanding of what concrete proof would look like and what kinds of observations are necessary to substantiate extraordinary claims. This iterative process of hypothesis testing and refinement propels scientific progress, pushing the boundaries of our knowledge and sharpening our investigative tools. As 3I Atlas continues its journey toward perihelion and beyond, the mounting observational evidence gathered from a variety of advanced instruments will be crucial in deciphering its true nature. The answers we seek, whether it is a naturally occurring comet, a biological seed from another star, or an artificial probe, depend on the data we collect and interpret in the coming months. The next 6 to 12 months could prove decisive, providing the definitive information needed to resolve these fundamental questions about this interstellar visitor, and by extension about the broader processes that shape planetary systems, the distribution of life in the galaxy, and the possible role of intelligence in cosmic evolution. Part 11. Upcoming Observations. On October 3, 2025, we reach a pivotal milestone in our exploration of 3I Atlas, as it draws within approximately 30 million kilometers of Mars. This close approach offers an extraordinary opportunity for detailed observation. The European Space Agency has confirmed that both Mars Express and the ExoMars Trace Gas Orbiter will coordinate their instruments to scrutinize this object during its passage. These spacecraft are equipped with high-resolution stereo cameras, color imaging systems, and specialized payloads designed for surface and atmospheric analysis. In addition, the Mars Reconnaissance Orbiter, renowned for its high-resolution imaging capabilities, is expected to join the effort, although scheduling conflicts with ongoing surface operations may limit its participation. Nonetheless, each instrument on board these spacecraft brings unique strengths. They can analyze the structure of the coma, the glowing envelope of gas and dust surrounding the object, identify jet patterns, and detect subtle color variations. These measurements could help distinguish natural outgassing caused by solar heating from any potential artificial emissions, should they exist. The proximity to Mars enables observations at wavelengths that are impossible to achieve from Earth-based telescopes, free from atmospheric distortion and with vastly improved spatial resolution. This close vantage point allows for continuous temporal monitoring of the outgassing behavior over multiple rotations of the object, revealing how its activity evolves as it interacts with the sun's warmth. Spectroscopic observations aboard these orbiters could detect emission lines from molecular species that remain hidden to ground-based observatories because of Earth's atmospheric absorption or limited spectral resolution. The identification of additional molecules, unusual isotopic ratios, or signatures that could suggest artificial origin would dramatically transform our understanding of 3I Atlas's true nature and origin. Each new piece of data collected during this critical passage will bring us closer to unveiling the secrets carried by this mysterious interstellar traveler. On the 29th of October, the celestial object known as 3I Atlas will reach its perihelion, its closest approach to the Sun, at approximately 1.36 astronomical units. This position places it directly behind the Sun from Earth's vantage point, creating a significant observational challenge. During this critical phase, when solar heating is at its peak and volatile sublimation would be most vigorous, Most ground-based telescopes and Earth-orbiting instruments will be unable to observe it directly. The sun's overwhelming brightness and the geometry of the alignment obscure our view, effectively concealing the object from our usual observational arsenal. Yet hope remains through the deployment of several space-based observatories strategically positioned at the Sun-Earth Lagrange Point 1, or within the inner regions of the solar system. These dedicated assets might be able to maintain a line of sight to 3I Atlas during its perihelion passage. Among them, the Parker Solar Probe, designed to study the Sun's outer atmosphere, and the upcoming polarimeter instrument intended to unify observations of the solar corona and heliosphere, could potentially observe the object at its most active and revealing moment. These observations would be crucial. They could capture 3I Atlas when its volatile materials are sublimating most intensely, possibly unveiling any technological signatures or artificial attributes that might be concealed at greater distances. The environment during perihelion is characterized by intense solar radiation, creating conditions ripe for the activation or response of hypothetical biological or technological components. If the object harbors any form of biological life, artificial systems, or engineered devices, the increased solar energy could trigger measurable responses, awakening dormant features or revealing signs of artificial control that are otherwise undetectable from afar. Such a moment would be an ideal opportunity to gather data on the object's physical and chemical behavior under extreme conditions, providing the clearest window yet into its true nature. Meanwhile, observations from Mars-based spacecraft could offer alternative vantage points. Although the geometry of the orbit and the relative positioning pose challenges for detailed analysis, multiple spacecraft positioned at different angles could work in concert. The combined data from these various perspectives would enable us to reconstruct three-dimensional models of the coma, its glowing cloud of gas and dust, and map out outgassing patterns with unprecedented precision. This multi-angle approach could reveal the structure and dynamics of the sublimation processes, offering insights into whether the activity aligns with natural cometary behavior or suggests an artificial origin. Looking ahead, early December of 2025 promises a return to the possibility of Earth-based observations. As 3I Atlas emerges from behind the Sun and moves outward to a distance of roughly 1.8 astronomical units, it will become accessible again to terrestrial telescopes. The James Webb Space Telescope, with its dramatically enhanced sensitivity, will be prepared to resume detailed spectroscopic analyses, capturing the faint signatures of molecules and elements that could indicate its composition and origin. Ground-based observatories worldwide will coordinate extensive monitoring campaigns to detect any changes in the object's chemical makeup, outgassing patterns, or physical structure resulting from the solar heating experienced during perihelion. The Vera Rubin Observatory's commissioning activities could further enable rapid high-cadence observations, tracking variations in brightness, morphology, and activity over short timescales. These post-perihelion measurements are vital. They can help distinguish between natural evolutionary processes and potential artificial manipulation. Typically, natural comets exhibit predictable shifts in volatile emissions, dust production, and coma chemistry after close approach to the Sun, following well-understood sublimation physics. Any deviations from these established patterns could serve as indicators of artificial control systems or biological responses to environmental stimuli, providing crucial clues to the object's true nature. By the 19th of December 2025, the geometry will be particularly favorable. At this point, 3I Atlas will be roughly 1.8 astronomical units from Earth, close enough for detailed scrutiny yet far enough to minimize interference from the Sun's glare. This optimal positioning allows us to leverage the full suite of humanity's most powerful astronomical instruments without the complications associated with solar proximity. The comprehensive data collected during this window will be instrumental in revealing whether the object's activity is consistent with natural cometary physics or if it exhibits anomalies suggestive of artificial origin. In sum, this upcoming perihelion passage offers a rare and invaluable chance to observe 3I Atlas at its most active and revealing phase. Multiple space-based and ground-based assets will work in concert, employing advanced imaging, spectroscopy, and modeling techniques to peel back the layers of mystery surrounding this interstellar visitor. The observations made during this period could hold the key to understanding whether we are witnessing a natural object, a potential technological artifact, or perhaps something even more extraordinary, an indication of intelligent activity or deliberate seeding from afar. In the upcoming phases of our interstellar visitor's journey, an extraordinary observational campaign is set to unfold, harnessing the full power of humanity's most advanced space-based telescopes and ground-based observatories. The Hubble Space Telescope and the James Webb Space Telescope will work in concert, conducting comprehensive spectroscopic surveys that span from the ultraviolet through the infrared spectrum. These detailed observations are poised to detect subtle isotopic signatures which could reveal the formation environments of the object and identify organic compounds indicative of prebiotic chemistry, molecular structures that hint at the potential for life's building blocks. Moreover, the spectroscopic data might uncover artificial emission lines, subtle indicators of technological origins, suggesting the presence of engineered or even intelligent systems. Complementing these space-based efforts, terrestrial facilities such as the Very Large Telescope, the Keck Observatory, and the Atacama Large Millimeter-Sub-Millimeter Array will contribute additional observations across a broad wavelength range, from radio waves to optical light. This coordinated multi-platform approach will constitute the most comprehensive investigation ever attempted of an interstellar object under optimal viewing conditions, maximizing our chances of unraveling its mysteries. Looking ahead, March 16, 2026 marks a pivotal moment in this investigative saga. On this date, the object, designated as 3I Atlas, will approach within approximately 0.36 astronomical units of Jupiter, embarking on its final, most detailed encounter within the solar system. Such a close pass offers unprecedented opportunities to leverage the assets of the Jupiter system itself, including potential observations of the object from orbiting spacecraft and planetary assets. However, real-world operational constraints, such as fuel limits, safety protocols, and competing science priorities, significantly restrict the feasibility of modifications to spacecraft trajectories. There have been proposals suggesting that NASA's Juno orbiter could, in theory, adjust its path to observe 3I Atlas during this Jovian flyby. Yet these ideas currently remain purely hypothetical, as no formal approvals or mission extensions have been granted. The logistical challenges, fuel restrictions, operational risks, and mission priorities render such maneuvers highly unlikely unless compelling evidence of extraordinary phenomena emerges. Concurrently, the spacecraft Psyche, en route to its asteroid target, might opportunistically provide remote sensing data if the right geometric alignments occur favorably. Similarly, the European Space Agency's Jupiter Icy Moons Explorer JUICE mission could potentially observe the interstellar visitor from a distance. While these observations would be secondary science objectives rather than primary targets, they could still yield valuable data. The close approach near Jupiter uniquely presents opportunities for gravitational physics experiments as well. Precise tracking of 3I Atlas's trajectory during this encounter could reveal minute deviations from predicted gravitational paths, anomalies that might hint at artificial propulsion systems or unusual mass distributions within the object's nucleus. Such deviations could serve as compelling clues pointing toward non-natural origins. Furthermore, the intense radiation environment surrounding Jupiter might activate or disturb hypothetical biological or technological components embedded within or associated with the object, which otherwise remain dormant during interstellar space travel. Artificial systems engineered to operate under extreme radiation conditions could reveal themselves during this phase, whether through unexpected emissions, behavioral anomalies, or other signatures, providing crucial data points in our ongoing investigation. The scope of these efforts is reflected in the extensive list of instruments and assets that will be employed in the campaign. It reads like an inventory of humanity's most sophisticated space-based tools. The Hubble Space Telescope, James Webb Space Telescope, Transiting Exoplanet Survey Satellite, Neil Gorell's Swift Observatory, Sphere X, Mars rovers and orbiters, Parker Solar Probe, the Solar and Heliospheric Observatory, Europa Clipper, the Jupiter Icy Moons Explorer, the Lucy mission, and the Psyche spacecraft. This unprecedented multi-agency collaboration spans diverse scientific disciplines and international space agencies, demonstrating the extraordinary level of coordination dedicated to unraveling the nature of this interstellar visitor during its close approach. All these instruments working together aim to gather a wealth of data that could potentially answer fundamental questions about the object's origin, composition, and physical properties. The upcoming encounter promises to be a landmark event, a convergence of technological prowess and scientific curiosity, designed to probe the very nature of a visitor from beyond our solar system, and perhaps even to uncover signs of artificial intelligence or extraterrestrial engineering lurking within its form. This monumental collaborative effort exemplifies the scientific community's deep recognition that the passage of 3I Atlas presents an unparalleled opportunity to deepen our comprehension of interstellar objects, planetary formation mechanisms, and potentially groundbreaking insights into the presence of life or intelligence beyond Earth. The carefully orchestrated sequence of observations is designed to rigorously test multiple hypotheses regarding the true nature and origin of this enigmatic visitor. Initial observations near Mars establish baseline activity patterns, providing critical data on the object's behavior in a relatively mild environment. As the object approaches perihelion, the focus shifts to examining its response to extreme solar heating, with the perihelion passage itself serving as a natural experiment to observe how its physical and chemical characteristics change under intense thermal stress. Following perihelion, Earth-based observations are employed to monitor for evolutionary transformations, tracking how the object's structure and activity evolve over time in response to the shifting environment. The final observational phase occurs during the encounter with Jupiter, offering invaluable insights into the object's gravitational dynamics and its interactions with high radiation environments. This close approach acts as a definitive test of its mass distribution, structural integrity, and potential signs of artificial modifications. Each phase of this complex campaign is tailored to leverage specific capabilities while also contending with inherent limitations. Mars orbiters provide high-resolution imaging but are limited in their spectroscopic range, whereas Earth-based telescopes deliver broad spectral coverage but are hindered by atmospheric interference. Space-based instruments free from atmospheric distortion excel in spectral precision, yet are constrained by wavelength-specific sensitivities dictated by their design. Coordinating such a multifaceted observational effort across multiple international agencies, each with their own schedules and priorities, represents an extraordinary achievement in global scientific collaboration. The task of scheduling observations on highly oversubscribed facilities, managing synchronized data collection, and orchestrating joint analysis efforts requires a level of cooperation unprecedented in planetary science. Over the course of approximately 8 months, humanity's most advanced astronomical instruments will systematically track and study 3I Atlas during its journey through our solar system. Never before have we possessed such a comprehensive surveillance system capable of observing an interstellar visitor across multiple phases, from initial detection to final departure. The volume of data anticipated from this campaign is staggering, necessitating the development of innovative approaches in data storage, processing, and interpretation. Cutting-edge technologies such as machine learning algorithms, automated spectral analysis tools, and collaborative data-sharing platforms are being tailored specifically to handle this unprecedented influx of information. The true scientific value of this extensive observational effort hinges entirely on what the collected data ultimately reveal about the fundamental nature of our visitor. Whether it is a natural cosmic debris, a deliberately engineered artifact, or something yet beyond our current understanding. Equipped with the most sophisticated instruments ever assembled by humankind, scientists stand on the brink of potentially revolutionary discoveries about the origins and evolution of planetary systems, the distribution of life across the cosmos, and the role of intelligence in galactic development. The upcoming phases of investigation will critically assess the capabilities of these remarkable tools to detect signatures that could distinguish natural phenomena from extraordinary artificial or biological sources. Signatures that continue to captivate both scientific inquiry and public imagination alike. Particularly intriguing is the potential of isotopic spectroscopy, considered one of our most powerful methods for tracing the origins of 3I Atlas within the galaxy's sprawling chemical landscape. By analyzing the ratios of stable isotopes, such as deuterium to hydrogen, carbon minus 13 to carbon minus 12, nitrogen minus 15 to nitrogen minus 14, and oxygen minus 18 to oxygen minus 16. Scientists can glean vital clues about the environment in which the object formed. These isotopic fingerprints serve as a cosmic barcode, revealing the specific stellar conditions, chemical processes, and evolutionary history associated with its birthplace. As this campaign progresses, the detailed isotopic analysis promises to provide some of the clearest insights yet into whether 3I Atlas is a native relic from our galaxy's formation or a visitor from a distant stellar system, carried across the cosmos as part of a larger exchange of material and perhaps even biological information. The ratios of various isotopes, such as deuterium to hydrogen in water vapor, carbon-13 to carbon-12 in carbon dioxide, nitrogen-15 to nitrogen-14 in cyanogen, and oxygen-18 to oxygen-16 in different compounds, serve as highly specific chemical fingerprints. These signatures preserve detailed information about the conditions under which the object formed, offering a window into its environmental and geological history across vast timescales. Each stellar system imparts its own unique isotopic signature, shaped by the particular nuclear processes, chemical evolution, and environmental factors active during the epoch of planetary formation. Notably, if the object's isotopic ratios differ significantly from the norms observed within our solar system, it would suggest that it originated around a star with a different mass, metallicity, or evolutionary stage. Such deviations could provide crucial constraints on the precise birthplace of the object, as well as insights into its journey through interstellar space. Among these isotopic indicators, the deuterium to hydrogen ratio stands out as especially diagnostic because of its dramatic variability across different cosmic environments. Formation in the cold outer regions of a protoplanetary disk tends to produce higher deuterium enrichment, whereas warmer inner system conditions typically result in lower ratios. Moreover, these ratios are not static. They can be further modified by interstellar processing mechanisms such as selective photodissociation, where ultraviolet radiation breaks molecules apart, and chemical fractionation, which alters isotopic ratios during chemical reactions. Tracking the evolution of gas phase chemistry provides an additional powerful diagnostic tool for distinguishing between naturally occurring sublimation physics and potential artificial control systems. In natural comets, for instance, the sublimation process follows predictable patterns. As solar heating penetrates deeper into the nucleus, the ratios of volatile gases, like carbon dioxide to water, or the production rates of carbon monoxide, change in systematic temperature-dependent ways. These emergence patterns serve as benchmarks for natural activity. Conversely, if an object's chemical evolution deviates from these expected temperature-driven trends, exhibiting, for example, controlled volatile release, emission sequences timed to specific conditions, or chemical compositions that remain unchanged despite increasing solar heating, such anomalies could indicate active management or artificial intervention rather than passive thermal sublimation. The advent of the James Webb Space Telescope, with its unprecedented spectroscopic sensitivity, dramatically enhances our ability to detect faint molecular signatures that were previously beyond reach. This space-based infrared observatory can identify complex organic molecules, unusual isotopic variants, or artificial emission signals that may reveal artificial origins or engineered processes. Its capacity to analyze trace species with exceptional detail opens new avenues for distinguishing natural phenomena from potential signs of technology. Finally, measurements of non-gravitational accelerations, tiny deviations from expected orbital motion, offer one of the most direct tests for the presence of artificial propulsion systems. By combining high-precision astrometry with occultation timing techniques, scientists could potentially detect thrust-like signals as small as approximately 10 to the negative 13th of an astronomical unit per day squared. This level of sensitivity approaches the fundamental physical limits set by solar radiation pressure and the forces generated by natural outgassing. If persistent directional accelerations are observed that cannot be explained by sublimation-driven forces, such a finding would constitute compelling evidence for active, possibly technological propulsion. These measurements would be definitive in assessing whether the object employs artificial means of control, providing critical clues about its true nature and origin. The current data sets revealing no signs of anomalous accelerations in the trajectory of 3I Atlas suggest one of two possibilities. Either the object originates from natural cosmic processes, or any hypothetical artificial propulsion systems it might possess are so subtle that their effects are currently below our detection threshold. As observational techniques advance and measurement precision improves during upcoming phases of scrutiny, these constraints are likely to be refined significantly, potentially revealing minute deviations or confirming their absence with greater confidence. One of the most promising avenues for detecting signs of active control involves analyzing the morphology of the comet's coma through high-resolution, rapid sequence imaging obtained from orbiting spacecraft around Mars. Such detailed imagery could uncover periodic jet patterns, geometric symmetries, or sun-independent structures, features that would strongly suggest the presence of engineered propulsion or manipulation systems rather than passive thermally driven activity. Typically, natural comets exhibit jet activity that correlates with their rotation periods and solar heating cycles following predictable patterns governed by well-understood thermal physics. In contrast, artificially controlled jets might operate on timing sequences disconnected from these natural patterns, maintain pointing directions inconsistent with local temperature gradients, or display brightness variations that follow programmed routines rather than physical sublimation processes. Thanks to the high spatial and temporal resolution afforded by observations from Mars-based platforms, scientists can conduct detailed analyses of jet behavior that are simply impossible to achieve with Earth-bound telescopes. The European Space Agency's mission planners have confirmed that the Mars Express orbiter, along with the ExoMars Trace Gas orbiter, possesses imaging capabilities precise enough to detect jet structures down to scales of roughly 1 kilometer during the upcoming close approach on October 3rd. This resolution allows for morphological investigations comparable to those performed in detailed studies of comets within our own solar system, providing a wealth of data to discern natural activity from potential artificial signatures. In addition to jet morphology, dust polarimetry, the measurement of polarization properties of scattered light, is continuing to map the negative polarization branch and phase angle behavior of 3I Atlas. These optical characteristics serve as fingerprints of the dust grains composing the coma, revealing fundamental details about their size distributions, porosity levels, compositional variations, and internal structures. Such parameters are crucial for understanding the formation environment of the object, as they can carry signatures of the physical and chemical conditions under which the dust particles originated and evolved. Explaining the unusual polarization signatures through natural mechanisms involves considering processes such as exotic grain processing during their extended interstellar journey, formation in environments with dust condensation physics differing from those in our solar system, or compositional differences reflecting the unique stellar chemistry of their parent systems. Alternatively, if the dust particles are engineered, designed with specific optical or physical properties, the observed polarization behavior could be a consequence of deliberate manipulation. However, distinguishing between these natural and artificial origins based solely on polarimetry remains challenging, as similar optical signatures can arise from vastly different formation scenarios. To enhance the diagnostic power, scientists are combining polarimetry with other investigative techniques, looking for complementary indicators that might provide a more definitive classification. The detection of metals and organic molecules within the coma is another critical frontier. Improving the sensitivity and resolution of instruments dedicated to spectral analysis could yield decisive evidence, either supporting a natural origin or hinting at artificial processing. Currently, the detection of nickel signatures without corresponding iron lines has sparked curiosity among researchers. While this pattern is intriguing, it remains consistent with natural excitation and abundance effects observed in some solar system comets and does not, by itself, serve as conclusive evidence for artificiality. Looking ahead, future observations aim to identify additional metallic species, complex organic molecules, and isotopic variants. The presence of these molecules and isotopic ratios could help determine whether the comet's chemistry results from exotic natural processes, such as formation in chemically distinct stellar environments, or from artificial engineered origins involving deliberate chemical modifications. The pursuit of such detailed spectral data promises to deepen our understanding of the composition and history of this interstellar visitor, sharpening our ability to distinguish between natural cosmic phenomena and potential signs of extraterrestrial engineering. The potential discovery of unmistakable molecular signatures, complex compounds that defy the known chemistry of our universe, would serve as irrefutable evidence of an artificial technological origin. With the advanced capabilities of the James Webb Space Telescope, especially its heightened sensitivity to faint signals, scientists may soon detect intricate organic molecules that align with prebiotic chemistry, supporting hypotheses like panspermia, the idea that life's building blocks are distributed throughout the cosmos. Conversely, the detection of signatures characteristic of artificial biochemistry, such as complex organic structures indicative of biological cargo, would strongly suggest deliberate or engineered origins. However, differentiating between natural and artificial organic compounds is a task that surpasses current observational limits, requiring highly detailed molecular analyses. Such distinctions depend on identifying specific molecular arrangements, isotopic ratios, or chemical markers that are impossible to produce through natural cosmic processes alone. This necessity for precise molecular fingerprinting underscores the importance of future technological advancements and analytical methods. As evidence accumulates, our interpretive framework branches into three main scenarios, each with distinct implications. The first, outcome A, posits that the object is a naturally occurring comet with an unusual yet explainable chemistry. This would broaden our understanding of the diversity among interstellar objects, confirming that a wide range of chemical compositions can arise from cosmic material exchange and formation processes consistent with established physics. Such a case would position 3I Atlas as a valuable calibration point for models of interstellar object populations, enriching our knowledge base without upheaving current paradigms. Its significance rooted in expanding our catalog of cosmic diversity rather than revolutionizing our notions of life or intelligence. Outcome B offers a different perspective, suggesting that the object is a seed-like entity formed from natural processes but supporting the concept of cosmic material exchange as a mechanism for planetary development. This aligns with Suzanne Falsner's hypothesis that interstellar objects can serve as carriers of planetary seeds, actively participating in the assembly of planetary systems rather than merely being transient curiosities. Such a scenario would represent a profound shift in planetary science, demonstrating that interstellar objects can influence the architecture of planetary systems and explain observed correlations, such as the link between stellar mass and the frequency of planets, without invoking intelligent intervention. It would imply that natural seeding via cosmic materials is a fundamental process shaping planetary diversity across the galaxy. Outcome C, the most extraordinary and least probable based on current evidence, envisions the detection of unmistakable technological signatures, indicators of artificial origin, such as engineered molecular structures, deliberate emission patterns, or signs of advanced manipulation, pointing to extraterrestrial intelligence or engineering capabilities far surpassing human technology. Such a discovery would carry profound implications, redefining our place in the universe and igniting a paradigm shift in science, philosophy, and policy. Yet the high standards for proof mean that extraordinary claims demand extraordinary evidence. A single ambiguous or marginal signal would be insufficient. Confirmed technological signatures would require verification from multiple independent observational campaigns, employing various instruments and analytical techniques to rule out natural explanations convincingly. The stakes of misclassification are immense. A false positive, mistakenly declaring an artifact as artificial, could undermine the credibility of scientific research for decades and provoke inappropriate policy responses. Conversely, failing to recognize genuine signs of extraterrestrial technology could mean missing the most transformative discovery in human history. Therefore, rigorous standards, reproducibility, and cautious interpretation are essential in advancing our understanding of such phenomena. Should the final verdict on 3I Atlas affirm it as a naturally occurring comet, distinguished by its unusual chemical makeup, the ramifications for our scientific understanding would reach well beyond mere classification. Such a conclusion would compel us to fundamentally rethink and recalibrate our existing models of cometary diversity, the chemistry of the outer regions of stellar systems, and the statistical frameworks that describe the distribution of interstellar objects across our galaxy. In particular, the dominance of carbon dioxide, coupled with evidence of early water activity alongside its exotic dust properties and distinctive chemical signatures, would mandate the creation of new categories within comet taxonomy. Categories that are rooted in, yet extend beyond, the solar system-centric classifications we currently use. This expanded framework would better equip us to comprehend the chemical and physical diversity we expect from objects originating around stars of varying masses, metallicities, and evolutionary histories, thus refining our understanding of how different stellar environments influence the makeup of ejected material. Furthermore, models of outer system chemistry would require significant revision to account for the formation conditions that could produce 3I Atlas's particular volatile ratios and dust characteristics. By studying these parameters, especially those associated with carbon dioxide-rich comet formation, we could glean valuable insights into the stellar environment parameters that foster such unusual compositions. These insights would, in turn, inform and refine theoretical models of planetary system formation across diverse galactic contexts, illuminating how different conditions lead to the variety of planetary architectures and compositions observed or hypothesized. The importance of detailed analysis of a well-characterized interstellar object like 3I Atlas cannot be overstated. Its size distribution, chemical diversity, and activity level throughout its journey through our solar system would serve as key data points, providing crucial constraints on the overall population of interstellar objects. Such data would enable us to refine estimates of their total density within our galaxy and the frequency with which they encounter planetary systems, statistics vital for understanding the broader role these objects play in galactic material exchange and planetary seeding processes. These improved population models would directly influence and sharpen our theories of planetary formation. Higher inferred densities of interstellar objects would bolster arguments supporting material exchange and seeding between stellar systems, suggesting a galactic ecosystem where such exchanges are common and perhaps integral to planetary evolution. Conversely, lower densities might support the view that planetary systems are more isolated, evolving largely in situ without significant external material influence. If evidence continues to support the planet seed hypothesis, whether through 3I Atlas serving as a representative example or via broader population analyses, the implications could be nothing short of revolutionary. Such support would introduce a paradigm shift, positioning rapid core formation, possibly driven by captured interstellar objects, as a central mechanism in planetary development. This would provide a compelling explanation for observed correlations, such as the relationship between stellar mass and the occurrence of giant planets, fundamentally altering our understanding of how planetary systems form and evolve across the galaxy. This natural mechanism for seeding planetary systems offers an elegant solution to the long-standing timeline challenge that has troubled traditional core accretion models for decades. Instead of relying solely on the slow, incremental process of dust grains colliding and gradually building up planetary cores, the importation of preformed, ready-made cores could accelerate the formation of giant planets to occur well within the limited lifespans of protoplanetary gas disks, regardless of the star's size or type. Such a framework would also naturally account for the astonishing variety of chemical compositions observed in the atmospheres and overall makeup of exoplanets. If planetary cores are imported from diverse stellar environments, carrying distinct chemical signatures from their birthplaces, they would generate planetary systems with compositions that surpass what could be achieved through local formation processes alone. This idea of seeding thus not only addresses formation speed but also predicts a broader chemical diversity across planetary systems. Furthermore, the seeding hypothesis leads to specific testable predictions about the architecture of planetary systems. By correlating data on stellar cluster memberships with exoplanet survey results, scientists could verify whether stars born in dense, massive clusters indeed show a higher efficiency in forming giant planets compared to stars that originated in more isolated environments. Such correlations would provide critical evidence supporting the idea of interstellar core transfer as a common planetary building process. The implications of confirming an artificial origin for these interstellar objects would be profound, surpassing all previous scientific breakthroughs in scope and significance. It would revolutionize planetary defense strategies, as we would need to adapt our protocols to recognize that maneuverable, artificially generated objects could transit our solar system, rendering existing deflection methods, designed under the assumption of natural, predictable trajectories, ineffective. In addition, the search for extraterrestrial intelligence would shift away from passive listening approaches, such as radio surveys, toward active monitoring of anomalous objects within our solar system. The routine transit of alien technology would demand new detection strategies and protocols for potential contact, transforming our approach to the search for extraterrestrial life and intelligence. On a geopolitical level, the discovery of artificial interstellar objects would present unprecedented diplomatic and legal challenges. Questions surrounding territorial jurisdiction, rights to research and examine these objects, potential communication efforts, and threat assessments would necessitate the development of entirely new international frameworks, akin to a cosmic code of conduct, governing how humanity responds to these extraordinary visitors. In terms of technological development, the situation would likely propel the urgent creation of dedicated interception systems modeled after concepts like the European Space Agency's Comet interceptor. Pre-positioned assets placed in the outer solar system could enable rapid close-range analysis of new interstellar objects, providing data impossible to obtain through remote observation alone. Considering the logistical and engineering advantages, Mars-based launch platforms might become prime locations for intercept missions. With lower gravity and more favorable orbital dynamics, Mars could serve as an ideal launch pad for missions aimed at intercepting and studying interstellar objects shortly after their discovery. Developing such capabilities would represent a natural evolution from current Mars exploration infrastructure, transforming it into a hub for active interstellar object investigation, an essential step in preparing humanity for encounters with potentially deliberate extraterrestrial probes or artifacts. The advancements in our data collection and analysis culture, especially through the comprehensive investigation of interstellar objects like 3 Atlas, are extending well beyond the realm of isolated scientific breakthroughs. They are fundamentally transforming the methods by which we coordinate and execute large-scale, multinational astronomical observations. The protocols and organizational frameworks developed during this campaign serve as invaluable templates for future endeavors, enabling seamless collaboration among diverse space agencies, research institutions, and observational platforms. This campaign's success in coordinating efforts across countries and institutions ranging from ground-based observatories to space telescopes has demonstrated the immense value of maintaining extensive, well-organized archives of astronomical data. Initiatives like the Atlas Survey, the Wiki Transient Facility, and the Transiting Exoplanet Survey satellite have shown that having a robust, comprehensive database is crucial. Such repositories extend the observational baseline, allowing scientists to track the evolution of celestial phenomena over longer periods and refine trajectory calculations with increased accuracy. They also provide critical constraints on activity patterns, helping to distinguish between natural and potentially artificial signatures. The rapid and effective international coordination established during this investigation sets a clear precedent for responding to future discoveries that demand urgent, coordinated follow-up observations. The communication protocols, data sharing agreements, and joint mission planning procedures cultivated during this campaign not only enhance our capacity to analyze interstellar visitors, but also pave the way for more responsive and collaborative exploration of other cosmic phenomena. Furthermore, the cooperation between major space agencies like the European Space Agency and NASA during the critical Mars observation phase, exemplifies how diverse organizational assets can be orchestrated toward common scientific goals. Such a collaborative model underscores the feasibility and benefits of cross-agency resource sharing, especially when swift action is required. This approach can be adapted and extended to a variety of contexts, whether for monitoring transient cosmic events, studying potentially hazardous objects, or investigating other interstellar phenomena, highlighting the importance of international cooperation in advancing planetary science and astrophysics. Beyond purely technical and operational advancements, these efforts carry profound philosophical implications. They challenge us to rethink our understanding of our place in the cosmos, moving beyond traditional notions of planetary formation and life detection to grapple with more fundamental questions about humanity's relationship to the universe's vast, interconnected networks of intelligence and biological distribution. If natural seeding processes, whereby materials or life itself are distributed across the galaxy, are confirmed or even seriously considered, they would revolutionize our conception of planetary systems. Instead of viewing these systems as isolated islands formed independently around individual stars, we would recognize them as collaborative creations, interconnected through chemical contributions, biological exchanges, and possibly even intentional seeding across cosmic distances and epochs. Earth's materials, for instance, might contain components originally forged around stars that completed their entire life cycles long before our Sun ignited nuclear fusion. This galactic mixing perspective dissolves the boundaries between local chemistry and extraterrestrial origins, revealing a complex heritage that links worlds separated by vast distances and immense stretches of time. In this view, planetary systems become nodes within an intricate web of cosmic recycling, networks that operate across geological and cosmological timescales. Such a paradigm shift elevates the concept of biological seeding to a galactic scale, positioning life itself not as an isolated phenomenon confined to individual planets, but as a distributed cosmic phenomenon. The implications for astrobiology and life detection strategies are profound, suggesting that life's distribution could be a galactic process rather than a purely planetary one. This perspective would dramatically expand our understanding of biological evolution, hinting at a universe where life is more widespread and interconnected than previously assumed. The possibility of artificial origins, evidence of intelligence operating on scales and timescales far beyond our current technological reach, would confront humanity with humbling yet inspiring realities. Such a discovery would illustrate the vast capabilities of advanced civilizations, extending our sense of what is possible across cosmic time. It would serve as both a humbling reminder of our technological limitations and a catalyst for expanding our visions of intelligence's potential, inspiring new avenues of thought about the future of human and extraterrestrial endeavors across the universe's grand timeline. The manner in which humanity would respond to verified artificial visitors from space would serve as a profound test of our collective ability to act in unison, to analyze with meticulous care, and to exercise prudent caution when faced with potentially far advanced extraterrestrial technology. Such a discovery could serve as a catalyst, sparking unprecedented levels of international collaboration, uniting nations in a shared quest for understanding. Or it could intensify existing rivalries, fueling competition over access, influence, and the secrets these visitors might hold. Yet beyond the immediate policy debates and scientific revelations, the ongoing investigation into the enigmatic object known as 3I Atlas has already showcased humanity's exceptional capacity for coordinated curiosity. It exemplifies our ability to undertake diligent analysis, to approach extraordinary possibilities with an open mind, all while upholding rigorous standards for evidence and verification. This process, regardless of what the final verdict may be regarding the true nature of the object, exemplifies the core strength of science itself, transforming seemingly inexplicable anomalies into profound understanding through patience, creative theorizing, and collaborative effort across disciplines and borders. It underscores that our pursuit of knowledge is a collective enterprise rooted in careful observation, open dialogue, and critical evaluation. The stakes involved extend well beyond a single discovery. They touch upon the very advancement of human understanding, the fostering of global cooperation, and the capacity of our species to confront cosmic mysteries that challenge and reshape our most fundamental assumptions about our place in the universe. Turning now to the philosophical dimension, we confront a question that strikes at the deepest heart of cosmic understanding. Do star systems exist as isolated islands of chemistry, each developing in splendid solitude? Or do they participate in an expansive interconnected network, an immense galactic garden where materials, organics, and perhaps even life itself are ferried between worlds? If interstellar objects routinely carry these essential ingredients across vast distances, then the very boundaries that once defined individual planets and stars begin to dissolve. Instead, worlds become collaborative creations, nodes within a grand interwoven web of chemical and biological exchange, spanning light years and epochs of geological time. This perspective radically transforms our understanding of planetary identity. No longer are planets isolated, self-contained entities. Instead, they are part of a larger, dynamic ecosystem, an intricate dance of matter and life shared across the galaxy. The atmosphere, oceans, and living systems of Earth could contain materials originally forged in the fiery death throes of stars that existed billions of years before our sun's birth. The implications reach far beyond theoretical astronomy, touching upon the very questions of origins, heritage, and our collective responsibility. These ideas challenge the traditional narratives of creation, suggesting instead that our world's building blocks might be part of a cosmic inheritance, a legacy shared and passed along through galactic collaboration. If worlds grow not in isolation but through a process of galactic cooperation, then the very meaning of home expands, no longer confined to a single planet but encompassing countless stellar siblings whose contributions span the vast stretches of cosmic history. From this vantage point, humility in our understanding of origin emerges as perhaps the most profound philosophical consequence of the cosmic seeding process. The long-held view that planetary systems are independent achievements of local physics and chemistry begins to fade. Instead, we recognize that planets, and perhaps life itself, may be co-authored by the galaxy, shaped by mechanisms operating on scales far beyond human comprehension. This viewpoint places Earth within a broader cosmic community, an interconnected web of mutual dependence and shared heritage that stretches across stars and epochs. It elevates our conception of kinship beyond biological bonds, extending it into geological and astronomical relationships. In this light, our origins are intertwined with the grand evolutionary story of the galaxy itself, and our understanding of ourselves must evolve accordingly, embracing a humbling awareness of our place within this vast, collaborative universe. We come to see ourselves not simply as the inevitable outcomes of terrestrial evolution, but as active participants woven into the vast interconnected fabric of galactic processes. Networks that link our world to star-forming regions countless thousands of light-years away. This perspective profoundly reshapes the fundamental question of what it means to be alive or lifelike. When considering the possibility that the enigmatic object known as 3I Atlas might harbor biological materials, biotechnological systems, or autonomous technological entities, the traditional boundaries we've relied upon become increasingly blurred. The clear-cut distinctions that once separated living organisms from complex machines are now becoming more arbitrary as our technological prowess advances toward replicating the very complexity of life itself. Contemporary scientific endeavors on Earth, particularly in synthetic biology, programmable matter, and artificial life, are already challenging long-standing categories. We are developing materials and systems capable of growth, reproduction, adaptation, and environmental responsiveness. Traits once considered exclusive to living beings, while remaining entirely artificial in origin. Such hybrid entities capable of evolving and functioning in ways akin to biological systems could revolutionize our understanding of life and machinery, especially when imagined in the context of interstellar exploration. In the vast, unpredictable environments encountered during journeys spanning millions of years between stars, these systems might possess extraordinary capabilities for adaptation, self-repair, and mission flexibility, traits essential for survival amid the cosmic unknown. In this light, the conventional boundary between biology and technology diminishes to the point of insignificance. What becomes paramount are the functions necessary for survival and operational effectiveness. If 3i Atlas harbors such hybrid systems, a notion that remains unsupported by current evidence, it would mark the first encounter with a form of technology that transcends our existing categories for classifying what is natural versus what is artificial. Such a discovery would compel us to reevaluate and expand our philosophical frameworks, those that define life, intelligence, and the nuanced relationship that binds them. This contemplation ties directly into the enduring enigma known as the Great Silence Paradox, the puzzling absence of detectable extraterrestrial intelligence despite the galaxy's vast scale and age. One compelling resolution to this paradox might lie in the dark forest hypothesis, which posits that advanced civilizations are extremely cautious about revealing their presence. In a universe where survival could depend on remaining hidden, they might employ sophisticated camouflage, deception, or misdirection, making their technology virtually indistinguishable from natural phenomena. These civilizations could routinely observe less advanced species like ours, while deliberately choosing not to make their existence known, thereby avoiding potential threats. The implications of this hypothesis for human conduct and interstellar communication are profound and complex. Should we confirm the existence of camouflaged alien technology, it raises critical ethical questions. Should we attempt to establish contact, risking detection, or remain silent, preserving our safety? The choice we make could be decisive for our species' survival in a galactic landscape governed by concealed powers and unspoken rules. Alternatively, the apparent silence we observe might not be due to concealment, but could stem from differences in communication methods, energy scales, or conceptual frameworks that surpass our current technological and intellectual capabilities, realms of understanding beyond our present reach. What might initially seem like an absence could, in fact, be a reflection of pervasive presence, operating through mechanisms so sophisticated or unfamiliar that we currently lack the capacity to detect or comprehend them. This profound uncertainty raises foundational philosophical questions about the delicate balance between cautious skepticism and open-minded curiosity. When faced with potential evidence of extraterrestrial intelligence or technology, deciding whether to actively seek contact or to refrain from intervention becomes an issue of existential consequence. Such a choice could shape humanity's future trajectory, influencing our long-term survival and evolution within what could be a bustling, perhaps crowded, galactic community. Existing protocols for the search for extraterrestrial intelligence, SETI, are built on assumptions that any alien civilization we might encounter would be benevolent, or at least neutral, in their intentions toward us. However, this presumption might be dangerously naive. If the galactic landscape is dominated by competitive, ambivalent, or even hostile intelligences, then the detection of cleverly camouflaged reconnaissance devices or stealthy probes could indicate scenarios far more complex and perilous than our current models envisage. The presence of such concealed technology would suggest a universe far more intricate and potentially threatening, challenging our simplistic notions of cosmic loneliness. Our prevailing narrative frameworks, which often hinge on the idea of a universe largely devoid of other intelligent life, would need a fundamental reassessment if objects like the Three-Eye Atlas or similar phenomena reveal widespread intelligence or biological distribution across the galaxy. Such discoveries would compel us to reconceptualize humanity's place in the cosmic hierarchy, prompting a philosophical and cultural shift in how we perceive our significance. Religious, spiritual, and philosophical systems would have to evolve to accommodate the unsettling reality that humanity might be just one among potentially millions of intelligent species. A realization that could either humble us or inspire a renewed sense of cosmic kinship. This paradigm shift would demand a reevaluation of what it means to be unique or significant in the universe. If intelligent life is common rather than rare, the very notions of human achievement and exceptionalism would need to be redefined within a broader context where life and intelligence are widespread phenomena. Such a transition could evoke feelings of humility, prompting us to recognize our modest place within an expansive cosmic community. Alternatively, it could serve as a source of inspiration, fueling our curiosity and drive to explore, understand, and participate in this broader galactic tapestry. Beyond the immediate scientific and cultural implications, these philosophical considerations extend into questions of our approach to discovery itself. How we investigate, interpret, and respond to phenomena that challenge our current understanding. Striking the right balance between skepticism and openness is essential. The investigation of objects like the Three-Eye Atlas exemplifies our species' extraordinary capacity to uphold rigorous scientific standards while remaining receptive to revolutionary possibilities. An intellectual harmony that is vital for navigating the unknowns of the cosmos. This process of inquiry embodies core philosophical values: collaborative exploration, evidence-based reasoning, and a careful distinction between well-founded fact and speculative hypothesis. Such methodological rigor provides a sturdy foundation for confronting even more extraordinary discoveries that the universe may reveal in the future. Furthermore, these considerations invoke a sense of responsibility and stewardship, recognizing that if worlds across the galaxy are interconnected through material exchange networks or intentional seeding processes, humanity might bear obligations to safeguard and continue these cosmic interactions. In an interconnected galaxy where cosmic processes and exchanges could influence the emergence and evolution of life, our actions, whether in exploration, contamination prevention, or preservation, carry ethical weight. We may find ourselves not merely as passive observers, but as active custodians of a universal ecosystem, with responsibilities extending beyond our planet to ensure the integrity and continuity of these galactic networks. This expanded awareness challenges us to consider our role within a much larger interconnected cosmic community, one where stewardship, curiosity, and ethical responsibility intertwine as we navigate the profound mysteries and opportunities that lie beyond our current horizon. The realization that Earth's chemical and potentially biological heritage may extend across vast galactic scales fundamentally redefines our ethical perspective, elevating it beyond conventional environmental stewardship to encompass a broader sense of cosmic responsibility. This expanded viewpoint suggests that our actions are not confined solely to terrestrial ecosystems, but could influence processes operating on a galactic level, shaping the formation of planets, the distribution of life's building blocks, and the evolution of cosmic environments over billions of years. Such a profound shift challenges the traditional anthropocentric worldview that places humanity at the center of the universe, instead inspiring visions of us as active participants, stewards and contributors in the grand tapestry of cosmic evolution. Rather than remaining passive observers of distant phenomena, we might, in fact, assume a more engaged role, influencing the very processes that lead to the birth of planets and the dissemination of life across the galaxy. This philosophical journey, sparked by investigations into enigmatic objects like the Three-Eye Atlas, extends far beyond mere curiosity about a single celestial visitor. It prompts us to confront fundamental questions about humanity's position within an interconnected cosmic web, about the ways we interpret reality, our responsibilities toward potential networks of intelligence and life that span the Milky Way, and how our actions could ripple through these ancient, vast systems. The scientific process itself exemplifies this shift in perspective. Its greatest value, perhaps, lies not only in providing definitive answers, but in expanding our capacity to ask better, deeper questions. This requires a delicate balance, maintaining rigorous skepticism to avoid unfounded speculation, while remaining genuinely receptive to possibilities that transcend our current understanding. As we near the conclusion of our investigation, evaluating competing hypotheses about the true nature and origin of Three-Eye Atlas, these philosophical considerations offer crucial context. They remind us of the profound stakes involved and encourage a broader appreciation of the implications, both scientific and ethical, inherent in our pursuit of knowledge. In this final stage of reflection, imagine that three diverging paths lie ahead within the cosmic forest, each leading to radically different understandings of our place in the galaxy's evolutionary story. Over months of unprecedented observation and analysis, we have accumulated enough evidence to evaluate which route offers the most compelling explanation for this mysterious visitor. One possibility is the Loeb comet interpretation, viewing Three-Eye Atlas as a chemically unusual but fundamentally natural object. This scenario grounds itself in the well-established principles of physics and chemistry, suggesting that the object's properties, such as its carbon dioxide dominance, early water activity, exotic dust signatures, and distinctive polarimetric features, are simply the result of formation in unique stellar environments. Such an interpretation would broaden our understanding of interstellar visitor diversity, demonstrating that objects formed around stars of different masses and evolutionary stages can display a wide variety of chemical compositions and physical behaviors. Accepting this natural origin would be scientifically valuable, as it would refine models of the population of interstellar objects and deepen our comprehension of the chemistry in the outer regions of other star systems. It would also expand the taxonomy of comets, establishing new categories that account for formation in environments far different from our solar system. This understanding would arise from solid physics-based reasoning, reinforcing the idea that the universe's diversity can be explained through natural processes without requiring extraordinary revisions to existing frameworks. On the other hand, there is the artifact interpretation, a hypothesis that, although currently lacking direct supporting evidence, if confirmed through the detection of unmistakable technological signatures, would represent one of the most groundbreaking discoveries in human history. This scenario envisions Three-Eye Atlas as an engineered object, a relic of an advanced civilization, perhaps a probe or a piece of extraterrestrial technology, designed to study, influence, or even seed planetary systems. Such a discovery would challenge our understanding of cosmic ecology and open new frontiers in the search for intelligence beyond Earth. While the current observations do not yet provide the smoking gun evidence for this artificial origin, the possibility remains tantalizing. If future data reveal definitive technological signatures, such as systematic non-gravitational accelerations, narrowband emissions indicative of artificial power sources, or structured jet activity inconsistent with natural physics, it could revolutionize our view of the cosmos, confirming that we are not alone in both life and technological advancement. This scenario would be the most momentous in the history of science, prompting profound questions about our place in an inhabited universe and the nature of cosmic civilizations. In summary, the evidence we have accumulated points toward a spectrum of possibilities. From a naturally formed interstellar comet with extraordinary but explainable chemistry, to a deliberately engineered artifact crafted by an intelligent species. Each interpretation carries profound implications, either expanding our understanding of natural planetary processes or opening the door to the reality of extraterrestrial intelligence. The path we choose to follow will shape our scientific theories, ethical outlooks, and our cosmic consciousness for generations to come. This scenario hinges on the necessity of acquiring extraordinary proof, evidence that current measurements have yet to reveal, but that, once uncovered, would fundamentally reshape every facet of human civilization. Should we confirm the existence of extraterrestrial technology, the consequences would be profound. Our strategies for planetary defense would be revolutionized. Research priorities within CD would be recalibrated. International space policies would need rapid adaptation. And our philosophical understanding of how intelligence is distributed across the cosmos would be dramatically expanded. Such a groundbreaking discovery would simultaneously humble humanity's technological achievements, highlighting our current limitations, while igniting expansive visions of what intelligent life might accomplish over galactic timescales, centuries, millennia, or even millions of years into the future. The idea that this object might be a planet seed presents an elegant natural mechanism for cosmic material exchange, a process that could radically alter traditional planetary formation theories without invoking biological or artificial explanations. This concept offers graceful solutions to long-standing timeline problems that have challenged the core accretion model, which struggles to explain how giant planets form rapidly enough within the limited lifespans of protoplanetary disks. Furthermore, it provides a compelling framework for understanding observed correlations, such as the link between stellar mass and the frequency of giant planets, suggesting that planetary systems may grow not in isolation, but through a form of galactic cooperation. According to this seeding hypothesis, planetary systems could develop via a vast interconnected recycling network across the galaxy, an intricate web of material exchange rather than a series of isolated local events. This paradigm shift transforms our conception of worlds from solitary entities into nodes within an enormous dynamic system spanning billions of years, where materials and perhaps even life are shared across stellar boundaries. Remarkably, this explanation remains firmly rooted in well-established physical principles, emphasizing that it does not require speculative new physics, but rather offers a natural, plausible process consistent with our current understanding of the universe. The inherent uncertainties in our present knowledge underscore the true nature of scientific discovery, a process of unfolding understanding driven by careful observation, rigorous analysis, and open inquiry. Critical upcoming observational milestones, such as the encounter with Mars on October 3rd, the perihelion passage on October 29th, renewed Earth-based observations in December, and a close approach to Jupiter on March 16th, may provide the decisive evidence needed to conclusively classify this object. Each of these events presents unique opportunities, equipped with specific capabilities designed to test competing hypotheses. High-resolution imaging from Mars orbiters could reveal jet structures, outgassing patterns that would favor a natural cometary origin, or perhaps show signs of artificial control. Monitoring during perihelion could detect responses to extreme solar heating, enabling us to distinguish biological activity, technological processes, or purely physical phenomena. Post-perihelion spectroscopy will be instrumental in tracking chemical evolution, helping to differentiate between organic-rich, naturally sublimating volatiles and sequences that appear to be actively managed or artificially controlled. Meanwhile, the Jupiter encounter offers the final critical tests, gravitational physics experiments that could detect minute deviations indicative of artificial propulsion, along with exposure to intense radiation environments that might activate dormant biological or technological components. All these observations taken together will form a comprehensive data set, each phase contributing vital clues to a puzzle that could redefine our place in the universe. As we await these upcoming milestones, we are encouraged to remain vigilant, carefully analyzing the data released by NASA, the European Space Agency, and other space agencies. Particular attention should be paid to diagnostic signatures, those subtle, telltale indicators that could distinguish natural origins from artificial or biological ones, guiding us toward the most accurate interpretation of this enigmatic object's true nature. Isotopic ratios pointing to extraordinary formation environments, subtle non-gravitational accelerations indicative of artificial propulsion, or intricate organic signatures suggestive of biological cargo would serve as pivotal evidence in assessing extraordinary claims about cosmic phenomena. The strength of the scientific method lies in its unwavering commitment to following the evidence wherever it may lead, all while upholding high standards that prevent hasty conclusions, especially when considering claims that challenge established understanding. The investigation of 3I Atlas exemplifies this delicate balance, maintaining an open mind to revolutionary possibilities without sacrificing rigorous skepticism that safeguards the integrity of scientific inquiry. Beyond the technical debates about classification and origin, 3I Atlas has already succeeded in broadening our perspective on the universe's hidden potentials, on phenomena that, at first glance, seem mundane but may, upon deeper examination, reveal profound truths. The process of investigation demonstrates science's remarkable capacity to turn what initially appear as anomalies into deeper insights, achieved through collaborative efforts that span disciplines and cross international boundaries. This collective inquiry underscores the power of science not only as a tool for discovery but as a philosophical practice that continually expands our understanding. Moreover, the implications extend far beyond the technical realm, touching upon fundamental questions of cosmic connectivity, the exchange of materials between worlds, and humanity's place within potentially vast, interconnected networks of galactic evolution. Whether these networks are driven by natural processes, artificial engineering, or some hybrid of both. In this context, 3I Atlas challenges long-held assumptions about the universe's insularity, about the rarity of life, and about the boundaries that define individual planetary systems. Concluding this exploration, we pose a thought-provoking question. Which discovery would prove most transformative for humanity's future and our cosmic comprehension? Would it be the realization that we live in a galaxy where worlds are routinely shared through natural mechanisms, an insight that could revolutionize our understanding of our planetary heritage and our ethical responsibilities within this cosmic web? Such a revelation would compel us to reconsider our role in the universe, perhaps prompting a shift towards active participation in what might be called cosmic gardening. Should evidence of extraterrestrial intelligence or activity be confirmed, it would demand an immediate and profound revision of our assumptions about human uniqueness and cosmic isolation. It might also necessitate a careful reevaluation of how we balance openness to contact with the need for caution in the face of potentially superior civilizations or technologies. These discoveries reveal that nature's operations are far stranger and more interconnected than current theories suggest, an insight that is both humbling and inspiring, pushing the boundaries of human knowledge and technological development. Every potential outcome of this investigation carries profound implications, shaping the trajectory of human civilization, guiding future scientific priorities, and redefining our philosophical frameworks about meaning, purpose, and responsibility within a universe that exceeds individual planetary boundaries. The process of collective judgment, embodying the democratic spirit of science, reflects our recognition that interpreting evidence ultimately depends on human discernment, community evaluation, and the wisdom that emerges from diverse perspectives and expertise. Through this ongoing inquiry, we acknowledge that the universe's secrets are vast and complex, demanding a careful, open-minded approach that balances skepticism with curiosity. In doing so, we stand to deepen not only our scientific understanding but also our philosophical outlook, transforming the way we see ourselves within the grand cosmic tapestry. We assure ongoing coverage as new, critical data emerges from a series of pivotal observations, ranging from the detailed scrutiny of Mars-based measurements and perihelion tracking, to post-perihelion spectroscopic analysis and the upcoming encounter with Jupiter. The narrative of scientific discovery is continually unfolding, driven by the most extensive and collaborative investigation of an interstellar object ever undertaken by human ingenuity and international cooperation. As this process advances, the comment section transforms into a vibrant forum, a space where the community can engage in meaningful dialogue about how to interpret the mounting evidence, evaluate competing hypotheses, and contemplate the profound philosophical questions that extend well beyond mere classification. These questions probe the very essence of humanity's cosmic position and our evolving relationship with potentially vast networks of galactic intelligence or biological exchange, concepts that challenge our deepest understanding of life, matter, and the universe itself. Regardless of what the ultimate nature of 3I Atlas may be it a naturally occurring comet, an artificially constructed probe, a biological courier, or a planetary seed, it has already demonstrated the universe's remarkable capacity for phenomena that surpass our current scientific comprehension. This enigmatic visitor compels us to refine our questions, enhance our investigative tools, and broaden our conceptual horizons. It serves as a compelling reminder that cosmic mysteries are scattered across the galaxy's spiral arms, nestled within stellar nurseries and drifting silently through interstellar space. Areas where wandering travelers move between moments of destiny that could fundamentally reshape entire civilizations and redefine our understanding of our place within the grand cosmic evolutionary story. The journey of discovery continues as 3I Atlas moves toward its next rendezvous, heading first to Mars, then to the Sun, and ultimately to Jupiter, carrying with it the secrets of ancient worlds that first formed around distant stars in epochs long past. The solutions we seek are out there, awaiting those patient enough to follow the trail of evidence, remaining open to possibilities that transcend the limits of current human knowledge and stretch the boundaries of imagination. Indeed, the universe still holds countless surprises for those willing to look intently at visitors from the space between stars, reminding us that the cosmos is an endless frontier of discovery, where each new revelation challenges us to evolve our understanding and embrace the unknown.